Hello everyone and welcome to the BrainOmega channel. Today we're diving into a fascinating topic at the intersection of two powerful fields, graph neural networks and reinforcement learning. The source code is available in our GitHub repo. Grab it from the link in this video's description. We'll be building an agent that learns to play the classic game cart pole, but with a unique twist. Instead of feeding the game state directly into a standard neural network, we'll first represent it as a graph and then use a GNN to make decisions. This tutorial will walk you through the complete Python code, explaining every block step by step. By the end, you'll understand how to structure a graph reinforcement learning project. Let's get started. So, what's our goal? We're tackling the cart pole environment from OpenAI Gym. In this game, we have a cart that can move left or right, and our job is to balance a pole on top of it. The state, or the information we get from the game at any moment, is a simple array of four numbers: the cart's position and velocity, and the pole's angle and velocity. A traditional approach would feed these four numbers into a standard neural network, but we're going to do something different. We'll convert this array into a graph structure first, and then feed that graph into a graph neural network, or GNN. This allows our model to learn not just from the values themselves, but from the connections and relationships between them. Let's jump into the code, starting with graphmaker.py. Before we can build a graph, we need to define its components. This first function, construct sur index pairs, is all about defining the features for the nodes in our graph. Given our state of four numbers, this function creates specific pairings. First, it pairs adjacent elements, grouping cart position with cart velocity and pole angle with pole velocity. Then, it adds symmetric pairings, linking the cart's position with the pole's velocity and the cart's velocity with the pole's angle. For the cart pole state, this gives us four pairs of indices. Each of these pairs will be used to create a single node in our graph, where the node's features are the two state values indicated by the indices. Now that we know how to pair our state variables, let's look at the createGraphData function, which actually builds the graph. First, it creates the edge index. This defines the connections or edges between the nodes. By using permutations, we are creating a fully connected graph. This means every single node is connected to every other node, allowing the GNN to learn the maximum number of relationships. Second, it creates the node features, which PyTorch geometric calls X. It uses the index pairs from our previous slide to build a list of features for each node. So, our graph will have four nodes, and each node will have features consisting of a pair of values from the game state. Finally, it bundles the node features and edge connections into a data object, a standard container used by the PyTorch geometric library. Moving on to model.py, this is the brain of our operation. Let's look at how the graph reinforce agent is initialized. The most important layer is the graph convolution layer, which is a GCN-conv from PyTorch geometric. PyTorch geometric is a library built on top of PyTorch, designed specifically for deep learning on graphs and other irregular structures like social networks, molecular data, knowledge graphs, and more. This is what performs the graph convolution, allowing information to be passed between connected nodes. Note that its input dimension is 2, because each of our nodes has features made of two numbers. We also have standard linear layers, a layer normalization for stability, and an Adam optimizer to handle learning. Finally, we have experience memory. This is a list that will store the rewards and action probabilities from each step within a single episode. This is crucial for the reinforce algorithm, which we'll see soon. The forward method is where the agent makes a decision. It takes the graph's node features and edge index as input. First, the graph data is passed through our GCN-conv layer. This is where the network learns from both the node features and the graph's structure. Next, we use global add pool. This is a critical step. It aggregates the feature vectors from all the individual nodes into a single feature vector that represents the entire graph. This gives us a holistic summary of the game's state. After aggregation, this single vector is passed through a standard linear layer. Finally, we apply log softmax to the output. This gives us the log probability for each possible action. In Cartpole's case, the log probability of moving left and the log probability of moving right. After an episode finishes, the agent needs to learn from what just happened. This happens in the optimize method, which implements the reinforced policy gradient algorithm. First, it looks at the entire episode's history, which we saved in experience memory. It goes backward from the final step and calculates the discounted cumulative reward for each step. This means rewards earned earlier in the episode are worth more than later ones, thanks to the discount arm factor. Second, it normalizes these rewards by subtracting the mean and dividing by the standard deviation. This is a standard trick that makes training much more stable. Third, it calculates the policy loss. The formula is negative log probability times reward. The intuition is simple. If an action led to a high positive normalized reward, we want to increase that action's probability. If it led to a low negative reward, we want to decrease its probability. Finally, it backpropagates this loss to update the network's weights and clears the memory for the next episode. Now, let's bring everything together in main.py. This script orchestrates the entire process. First, we import our necessary libraries and our own graph data processor and graph reinforce agent classes. We create the Cartpole environment and set a device for our tensors using a GPU if one is available. We then set a random seed. This is crucial for reproducibility. It ensures that if we run the code multiple times, we'll get the exact same results. Next, we define our hyperparameters, the learning rate for the optimizer, the number of episodes to train for, and gamma, the discount factor for future rewards. Finally, we instantiate our graph reinforce agent and call our construct index pairs function once at the beginning to get the template for our graph nodes. The main training loop is the heart of our program. For each episode, we first reset the environment to get an initial state. Then, inside the while loop, which runs until the pole falls over, we have our agent environment interaction. Step 1. We take the current state from the game and use our create graph data function to convert it into a graph object. Step 2. We feed the graph's features and edges into our agent model. The model outputs log probabilities, which we convert to a probability distribution and then sample from to choose an action. Sampling allows the agent to explore different actions instead of always picking the most likely one. Step 3. We perform the chosen action in the environment. The game gives us back the next state, a reward, and a done flag. We store the reward and the log probability of the action we took in the agent's memory for the optimized step later. Once the while loop finishes, which means the episode is over, a couple of things happen. First, and most importantly, we call agent.optimize. This triggers the learning process we discussed from model.py, where the agent updates its GNN weights based on the entire episode's performance. We also record the total score for the episode. And finally, every 10 episodes or so, we print the average score over the last few episodes. This helps us track whether our agent is actually learning and improving over time. After all the training episodes are done, we close the environment. If all goes well, you should see the average score trending upwards. So, let's recap what we've accomplished. We successfully built a reinforcement learning agent that represents its environment state as a graph. We created a data processor to handle the state-to-graph conversion. We built a GNN-based agent that can take this graph and make decisions. We implemented the reinforce algorithm to allow the agent to learn from its experiences. And finally, we tied it all together in a main training loop. This project is a fantastic starting point. From here, you could try using more advanced graph layers like graph attention networks. Apply this technique to more complex environments where relationships between state variables are even more critical, or experiment with different ways of constructing the graph itself. I hope this tutorial has been helpful and has demystified the process of combining GNNs with reinforcement learning. Thank you so much for watching. If you found this video useful, please hit the like button, subscribe for more content, and feel free to leave any questions in the comments below. See you in the next one. Hello everyone, and welcome. Today, we're diving deep into one of the most powerful and scalable architectures in modern deep learning, the mixture of experts, or MoE. If you'd like to follow along or customize the code yourself, the complete source code is available on our GitHub. You can find the link in the description of this video. We'll go beyond the theory and build a complete working Mo model from scratch using PyTorch. Our model will use a CNN to extract features from images and then use an MoE transformer layer to perform classification. We'll break down every single component: the gating network, the experts, the load balancing loss, and the final training pipeline. By the end of this video, you'll have a solid understanding of how to implement and train your own MoE models. Let's get started. So, what exactly is a mixture of experts, and why is it so important? Imagine a giant monolithic neural network. To process any input, whether it's simple or complex, the entire network has to be activated. All those billions of parameters are used every single time, which is incredibly inefficient. The mixture of experts model proposes a smarter way. Instead of one giant, we have a collection of smaller, specialized networks called experts. Then, we have a lightweight gating network that acts like a router. For each input, the gating network quickly examines it and says, "Okay, for this specific data, I'm going to activate expert 1 and expert 4. The rest can stay dormant." This is called conditional computation. We get the representational power of a massive model, but only pay the computational cost of a much smaller one for each forward pass. This is the key to scaling models to trillions of parameters, like we see in large language models today. Let's start our code walkthrough with the simplest piece, the expert network itself. As you can see, an expert is nothing fancy. In our implementation, it's just a basic two-layer feed-forward neural network. It takes the input data, passes it through a linear layer, applies a ReLU activation function, and then passes it through a final linear layer. Each of our experts will be an instance of this same class. The idea is that through training, each one of these simple networks will learn to become a specialist on different types of features or patterns in the data. Now, for the most critical part of the MoE, the gating func, or the gating network. This module's job is to choose which experts get to see the input. Here's how it works. First, it takes the input X and passes it through a single linear layer. The output of this layer gives us a score or logit for each expert we have. Second, we use torch top k to find the indices and scores of the top k experts. In our case, k is 2. This is the top k routing strategy. We are deciding to only use the best 2 experts for this input. Third, we apply a softmax function only to the scores of these top experts. This turns their scores into a probability distribution, giving us the weights for combining their outputs. Finally, we create a sparse tensor. It's a tensor full of zeros, but we scatter the weights we just calculated into the positions corresponding to our top k experts. This gives us a final weight vector where only the chosen experts have non-zero weights. The transformer block with MoE is where we assemble all the pieces. In its initialization, we create a module list of our experts and instantiate our gating network. Now, let's look at the forward pass. First, we get the sparse gate weights from our gating network. This tells us which experts to use and how much to trust each one. Second, we pass the input x to all experts and stack their outputs into a single tensor. This might seem inefficient, but on modern hardware, running these small, identical operations in parallel is very fast. Third, we perform the core MoE operation. We multiply the expert outputs by their corresponding gate weights. Since the weights for non-selected experts are 0, their outputs are effectively nullified. We then sum the weighted outputs to get our final Mo output. Finally, we add a residual connection by adding the original input x back to the output and apply layer normalization, which are standard practices for stabilizing transformer-like blocks. There's a common problem with MoE models. The gating network can get lazy and learn to always send data to the same few favorite experts. This means the other experts never get trained, and our model doesn't reach its full potential. To fix this, we introduce a load balancing loss. This is an auxiliary loss function designed to encourage the router to spread the work out more evenly. Here's how we calculate it inside our MoE block. After getting the gate weights, we first calculate the average weight or dispatch probability assigned to each expert across the entire batch of data. Then we apply a formula that penalizes this distribution if it's not uniform. We'll add this load balancing loss to our main classification loss during training. This nudges the gating network to explore using different experts, leading to better overall model performance. Now let's put everything together into our final CNN-MoE transformer model. The architecture is a powerful and common pattern. First, we define a CNN feature extractor. This is a standard convolutional neural network whose job is to take a raw input image and convert it into a flat feature vector that captures its important visual information. Then, in our main model class, we chain the components together. An input image X first goes through the feature extractor. The resulting feature vector is then passed to our transformer block with the mixture of experts layer. This block processes the features and also returns our load balancing loss. Finally, the output of the MoE block is passed to a final fully connected layer, FCOut, which produces the classification scores for our different classes. Before we look at the training loop, let's quickly look at the config.py file. This is a very good practice in any machine learning project. Instead of hard coding values like learning rate or the number of experts directly into our model and training script, we define them all in this separate configuration file. This makes it incredibly easy to experiment. If we want to try training with 8 experts instead of 5, or use a different dataset like CIFAR10, we only need to change one line in this file without touching the main application logic. Here you can see we set our dataset, model dimensions, and training parameters like batch size and learning rate. Finally, let's look at the training loop, which is managed by our trainer class. The most important part is how we incorporate our special load balancing loss. Inside the loop for each batch, we first pass the images through our model to get the classification outputs and the load balancing loss. Then we calculate our total loss. This is the key step. The total loss is a combination of two things. The standard classification loss, which is cross entropy in our case, plus the load balancing loss we calculated earlier, multiplied by a small scaling factor called alpha. By adding these two losses together, we ensure that when we call loss.backward, the gradients will update the model weights to not only get the classification right, but also to encourage the gating network to distribute the load across all experts. The rest of the loop involves the standard steps of zeroing the optimizer, backpropagation, and updating the weights. So let's quickly recap what we've accomplished. We have successfully built a complete mixture of experts model from the ground up in PyTorch. We implemented the individual expert networks, the crucial top K gating function that routes data, and the important load balancing loss that ensures all our experts get trained. We then combined these into a full-fledged image classification model and created a configurable training script to run it. You now have a solid foundation to start experimenting with MOE architectures yourself. Try changing the number of experts, see how performance changes as you vary K, or apply this model to other computer vision datasets. Thank you so much for watching. I hope this deep dive was helpful. If you found value in this tutorial, please hit the like button, subscribe for more advanced deep learning content, and feel free to ask any questions in the comments below. Hello everyone, and welcome to the BrainOmega channel. Have you ever wished you had a personal assistant to take notes during your meetings? Well, today we're going to build one. You can find the complete code and examples on our GitHub page. Just check the link in the video description. In this step-by-step tutorial, we'll create a complete meeting minutes generator using Python. This powerful tool will take any meeting audio, transcribe it using OpenAI's Whisper, generate professional structured meeting minutes with a Llama 3.1 model, and finally, give us a downloadable PDF of the results. We'll cover everything from setting up the models to building the user interface. Let's dive in and build our very own AI meeting assistant. So, what's the big picture? Our application automates the entire process of creating meeting minutes. It starts when a user uploads an MP3 audio file of their meeting. This file is first sent to OpenAI's Whisper API, which is incredibly accurate at transcribing speech to text. Once we have the raw transcript, we send it to a Llama 3.1 model. This is where the real magic happens. We'll use a carefully crafted prompt to instruct the Llama model to act as a professional minute taker, organizing the messy transcript into a structured document with a summary, key discussion points, and clear action items. Finally, to make the output easy to share and store, our script will convert these generated minutes into a PDF file that the user can download directly. We'll use the Gradio library to create a simple and clean web interface for the whole process. Let's start with the code in meetingminutesgenerator.py. The init method is where we set everything up. First, we load our OpenAI API key from environment variables and define the names of the models we'll be using. Whisper 1 for transcription, and MetaLlama 3.18b instruct for generating the minutes. Now, here's a crucial part for making this run on consumer hardware. We're using the bits and bytes library to load the Llama model with 4-bit quantization. This dramatically reduces the model's memory footprint, allowing us to run this powerful 8 billion parameter model without needing a top-of-the-line GPU. We define the quantization configuration and then pass it to the from pre-trained method when loading our model. This is a key optimization for making large models accessible. Next up is the transcribe audio method. This function is straightforward but powerful. Its only job is to take the file path of our meeting recording and get it transcribed. We use a simple try except block for error handling. Inside the try block, we open the audio file in binary read mode. Then we make a call to the OpenAI Python client, specifically the OpenAI.audio.transcribe function. We pass it the model name we defined earlier, Whisper1, and the audio file itself. We also specify that we want the response format to be simple text. The API handles all the complex speech-to-text processing, and what we get back is a single string containing the full transcription of the meeting. This is the core of our application's intelligence, the generate minutes method. The magic here is all in the prompt engineering. We create 2 main pieces of text to guide the Llama model. First, a system message. This sets the persona for the AI. We tell it, you are a professional meeting minutes writer, and we give it very specific instructions on the format we want. a summary, discussion points, takeaways, and action items, all in Markdown. Second, we create a user prompt where we provide the raw transcript we got from Whisper. We combine these into a messages list, which is the standard format for interacting with instruction-tuned models. We then use our tokenizer to prepare these messages, generate a response from the model, and finally do a little bit of string cleaning to remove any special tokens from the model's output, leaving us with a clean, well-formatted Markdown document. Once we have our beautifully formatted Markdown text, we need a way to present it professionally. That's where the Generate PDF method comes in. This function uses the FPDF library, a simple and effective tool for creating PDFs in Python. We initialize a new PDF object, add a page, and set a standard font like Arial. The key component here is the multi-cell function. We loop through each line of our generated minutes and add it to the PDF using multi-cell. This function is great because it automatically handles text wrapping, so we don't have to worry about lines running off the page. Finally, we generate a unique file name using Python's UID library to avoid overwriting files, save the PDF, and return the file path. The process upload function is the main orchestrator of our backend logic. It's a Python generator function, which means it can yield values back to the user interface incrementally, allowing us to show real-time progress updates. First, it performs some basic input validation to make sure a valid MP3 file was uploaded. Then, it calls the methods we've already discussed in sequence. It calls transcribe audio to get the transcript, yielding a status update to the UI. If that's successful, it calls generate minutes to create the structured text, again yielding an update. Finally, it calls generate PDF to create the downloadable file and yields the final results, the markdown text, and the path to the newly created PDF file. This function neatly ties our entire pipeline together. Now, let's look at interface.py. A powerful backend isn't very useful without a user-friendly way to interact with it, and the Gradio library makes this incredibly easy. We define a launch interface function. Inside it, we create a gr.blocks layout, which gives us full control over the UI's structure. We add some titles using gr markdown. Then we define our core components, an audio input widget for uploading the MP3, a markdown output component to display the generated minutes, a file output component to provide the download link for the PDF, and a button to start the process. The most important line is submit button click. This single line connects our UI to our backend. We tell it that when the button is clicked, it should call the generator.process upload function, using the audio input as its input and sending the results to the markdown output and PDF output components. It's that simple to wire everything up. Last but not least, we have the main.py file. This script is as simple as it gets, and it has one job: to start our application. It imports the launch interface function we just created in our interface.py file. Then, inside the standard if name equals main block, it calls this function. This is the command that initializes our meeting minutes generator, builds the Gradio UI, and starts the local web server, making our application accessible in a web browser. To run our entire project, all we need to do is execute this one file. So, let's recap what we've built today. We've created a fully functional AI meeting assistant. It uses Whisper for highly accurate transcription, a quantized Llama 3.1 model with sophisticated prompt engineering to generate professional notes, and a PDF generator for a polished final output. And we wrapped it all in a simple interactive web application using Gradio. This project is a fantastic starting point. You could extend it by adding support for more audio formats, integrating speaker diarization to identify who said what, or swapping out the Llama model to experiment with other powerful language models. I hope this tutorial has been a valuable look into how different AI tools can be combined to create incredibly useful applications. Thank you so much for watching. If you found this helpful, please like, subscribe, and share. See you in the next one. Hello everyone, and a huge welcome to this coding adventure. Have you ever looked at incredible AI models like Llama or ChatGPT and thought, that's amazing, but how does it actually work? It can feel like magic, but today we're going to pull back the curtain and become the magicians ourselves. The full code is available on our GitHub. Check the link in the video description. In this video, we're not just going to talk about large language models. We are going to build one from the ground up using PyTorch. We'll write every line of code, understand every component, and by the end, you'll have a working mini LLM that you trained yourself. This is a hands-on journey from a blank script to a text-generating AI. So, grab your favorite drink, open up your code editor, and let's get started. Before we start coding, let's look at our roadmap. Building a language model is a journey with several key stops, and we'll be visiting every single one. First, we need to create our tokenizer. Think of this as teaching our computer a new language by creating a dictionary. It needs to know how to break down human text into numerical pieces it can work with. Next up is data preparation. Once we have our dictionary, we need to read our book, our text dataset, and convert the whole thing into a format the model can train on. We'll also create a system to feed it data in small, manageable batches. Then comes the main event, building the model itself. This is where we'll construct the transformer architecture, the brain of our operation, layer by layer. After that, we'll set up our configuration file. This is like the settings menu for our project, where we can easily tweak all the important numbers. With everything in place, we'll write our training script. This is where the learning happens. We'll feed the model data and watch it get smarter over time. And finally, the moment we'll all be waiting for, inference. We'll load our trained model and start a conversation with it, prompting it to generate new and original text. It's a complete journey, so let's take our first step. Alright, first stop, tokenizer.py. Our model can't read words like hello or world, it only understands numbers. The tokenizer is the translator that bridges this gap. We're using a library called sentence piece to train what's known as a byte pair encoding, or BPE, tokenizer. This is a really clever approach. Instead of just splitting by words or characters, it learns the most common subwords from our text. So it might learn that ing, the, and trans are very common and should be their own tokens. We call the train function and give it our text file. I'm using a Wikipedia dump here. We tell it the model type is BPE and set our desired vocab size, which is how many words we want in our dictionary. The most important argument here is byte fallback equals true. This is our safety net. It means if we ever encounter a weird symbol or a character from another language, our tokenizer won't crash. It will just fall back to representing it by its raw bytes. This makes our tokenizer incredibly robust. When we run this, we get two files, a .model file, which is the trained tokenizer logic, and a .vocab file, which is the dictionary it created. After training our tokenizer, it's always a good idea to make sure it works as expected. That's what these next two functions are for. Think of it as a quick sanity check. The load tokenizer function is our way of loading the trained .model file back into our program so we can use it. It creates a sentence piece processor object which has the encode and decode methods we need. The test tokenizer function puts it to the test. First, it takes a sample sentence and calls tokenizer.encode. This converts our human-readable string into a list of integers, according to the vocabulary we just trained. Then, it immediately calls tokenizer.decode on that list of integers. This should hopefully give us back our original sentence. Running this script and seeing the original and decoded text match perfectly gives us the confidence that our tokenizer is ready for action. Okay, our tokenizer is ready. Now we need to prepare our mountain of text data for training in datautils.py. First, look at the load or create data function. Tokenizing a large text file can take a little while, and we don't want to do it every single time we run our training script. So this function is a smart utility. The first time you run it, it reads your text file, encodes the entire thing into a long sequence of tokens, and saves it to a file called encoded data point t. Every subsequent time you run it, it will see that the file already exists and just load it directly, saving you a ton of time. Next, get train valid data does a simple but crucial 90-10 split. We'll use 90% of our data for training the model and hold back the remaining 10% for validation, which helps us check for overfitting. Finally, getBatch is our workhorse. At every step of training, the model needs a small chunk of data. This function goes into our dataset, randomly picks a few starting points, and slices out sequences of a fixed context length. It then creates X, the input, and Y, the target. Remember, Y is just X shifted one token over. The model's job is to look at a sequence of tokens in X and try to predict the corresponding token in Y at every single step. Now for the part you've been waiting for, model.py. We're starting with the absolute heart of the transformer, the head of self-attention. This is where the magic happens. Imagine a token is a person in a crowded room trying to understand a conversation. To do that, it needs to pay attention to other people. In our model, each token creates 3 vectors to help it do this: a query, a key, and a value. The query is like the token asking, "I'm a verb. Who around here is a noun that I might be related to?" The key is like every other token holding up a sign saying, "I'm a noun" or "I'm an adjective." The value is the actual meaningful content that each token holds. In the forward method, we first calculate the attention scores. We do this by taking the dot product of every token's query with every other token's key. This tells us how much each token should pay attention to every other token. But here's a crucial rule. In language, you can't know the future. A token at position 5 shouldn't get information from a token at position 6. That's where our trill mask comes in. We mask the attention scores to hide all future positions, ensuring information only flows from the past to the present. Finally, after a soft max to normalize the scores, we use these attention weights to create a weighted sum of all the value vectors. The result is a new, improved vector for each token that is now enriched with context from all the other tokens it paid attention to. So, a single self-attention head is great, but it's like having just one person trying to understand all the different relationships in a text. What if one head is good at finding subject-verb relationships, but another is better at linking pronouns to nouns? That's the idea behind multi-head attention. It's like having a team of specialists. The multi-head class simply creates a list of our head modules and runs them all in parallel on the same input. In the forward method, you can see we get a list of outputs, one from each head. Each head has focused on something different. We then torch.cat them together, effectively lining up all the specialist reports side by side. This concatenated result is now very rich, but it's also very wide. So we use a final combine linear layer to project it back down to our model's standard embedding size. We've successfully gathered information from multiple perspectives and fused it into a single powerful representation. After our tokens have gathered all this great context from their neighbors through multi-head attention, they need some time to process it. That's the job of the forward layer. You can think of attention as the communication step, and the feed-forward layer as the thinking step. This part of the network processes each token individually. If you look at the structure, it's a very standard 2-layer neural network. We take the output from our attention layer, project it to a much larger dimension, in this case 6 times larger, apply a GELU activation, and then project it back down. This expansion and contraction pattern gives the model more capacity to find complex patterns and nonlinear relationships within the features of each token. It's a simple but vital part of the transformer's power. Okay, team, let's assemble our Lego bricks. We've built the attention piece and the feed-forward piece. Now we'll put them together into a single, repeatable block. This transformer block is the fundamental unit that we will stack to create the depth in our network. The structure is very elegant and follows a consistent pattern. The input X comes in, and first it passes through a layer norm. Then it goes into our multi-head attention layer. The output of that is then added back to the original input X. This X plus is the famous residual or skip connection. It's incredibly important because it allows gradients to flow directly through the network during training, which makes it possible to train very deep models without them forgetting the original signal. After that first sublayer, the pattern repeats. The result goes into another layer norm, then into our forward layer, and finally through one more residual connection. This add and norm pattern is a cornerstone of modern deep learning architectures. Now for the grand assembly. In the GPT class, we take our block and stack it up to create the full model. Let's look at the init method. We start with 2 crucial embedding layers. The token embeddings layer converts our input token numbers into dense vectors, but the model also needs to know the order of the tokens. That's where positions embedding comes in. It provides a unique vector for each position in the sequence. Without this, our model would just see a jumbled bag of words. Then, we create our blocks by making a nn.sequential container with n layers copies of our block class. This is the deep part of our network. After the blocks, a final layer norm and a final linear layer project the output back to the size of our vocabulary, giving us a score for every possible next token. Finally, notice the init weights method. We're not just using the default random weights. We're applying a specific initialization scheme that is known to work well for training transformers, which helps our model converge more smoothly during training. Let's break down the 2 most important methods in our GPT class. First, the forward method. This is what happens during a single step of training. We take the input token IDs, look up their token embeddings and their position embeddings, and simply add them together. This combined vector, which now contains information about both what the tokens are and where they are, is then passed through our entire stack of transformer blocks. The final output, the logits, is a giant tensor of scores. If we're training, we're also given the targets. Our goal is to calculate how far off our predicted scores were from the actual correct next tokens. We do this using cross-entropy, which gives us a single number, the loss. The whole goal of training is to make this number as small as possible. Second is the generate method, which is the fun part. This is how we generate text. It works in a loop. In each iteration, it takes the text generated so far, passes it through the model to get the logits for the very next token, converts those scores into probabilities using softmax, and then samples a new token from that probability distribution. It then appends this new token to our sequence and repeats the process. This predict, append, repeat cycle is what allows the model to write text 1 token at a time. Let's take a quick look at config.py. This might seem like a simple file, but it's one of the most important for doing serious research and experimentation. Think of this as the main settings menu or control panel for our entire project. Every important number that defines our model or our training process is here. We have the architecture parameters like batch size, the context window, the embed size, and how many n layers and n heads to use. We also have our training hyperparameters like the learning rate. If you want to see what happens when you train a deeper model, you just come here and change n layers from 7 to 12. If you want to try a different learning rate, you change one line. This practice keeps our main code clean and makes running experiments incredibly easy and organized. Alright, it's time to put on our trainer hats and step into train.py. The main function here orchestrates our entire training run. It starts by loading our tokenizer and data. Then it instantiates our GPT model. Now, here's a neat professional trick in the optimizer setup. We're using AtomW, a fantastic modern optimizer, but we're not applying weight decay, a type of regularization, to all parameters equally. It's often found that applying it to biases or layer normalization parameters can be less effective or even harmful. So, we split our parameters into two groups. The first group gets the parameters with two or more dimensions, like the weights in our linear layers, and we apply our full weight decay to them. The second group gets the one-dimensional parameters, like biases, and we turn weight decay off for them. We also set up a cosine annealing LR scheduler. This will start with our initial learning rate and smoothly decrease it in a cosine curve over the course of training, which often helps the model settle into a better final minimum. Training a large model can take hours or even days. Imagine you're 10 hours into a 12-hour training run and your power goes out. It would be a disaster if you had to start over. That's why checkpoints are our saviors. This block of code checks if a checkpoint file already exists. If it does, it loads not just the model's weights, but also the state of the optimizer, the last iteration number, and the best validation loss achieved so far. This allows us to seamlessly resume training right where we left off. Next is the calculate loss helper function. This is how we'll periodically check in on our model's performance. Notice the first and last lines inside the function, model.eval and model.train. This is crucial. Model.eval tells PyTorch to turn off any layers that behave differently during training and testing, like dropout. This gives us a stable, deterministic loss value. After we're done evaluating, we always remember to switch back to model. Train mode to turn those layers back on for the next training step. All right, here we are at the engine room of our project, the main training loop. This is where the learning actually happens, step by step, for hundreds of thousands of iterations. At every single step, we do four things. First, we get batch to grab a fresh chunk of training data. Second, we do the forward pass. We feed the batch to the model and get back our loss. Third, we do the backward pass, which is where the learning occurs. We call optimizer.zeroGrad to clear out any old gradients. Then, loss.backward calculates the gradients for this specific batch. It figures out how to adjust each weight to reduce the loss. We then clip grad norm to prevent our gradients from becoming too large and unstable. Finally, optimizer.step actually applies the updates to the model's weights. Fourth, every so often, as determined by eval interval, we pause to evaluate the model. We print the validation loss, and if it's the best score we've seen so far, we save a new checkpoint. This loop is the rhythm of deep learning: forward, backward, update, evaluate, and repeat. After all that hard work training, it's time for the grand finale in inference.py. This script is all about interacting with our trained model. The setup is simple. We load our tokenizer and our best saved checkpoint file into our GPT model structure. The most important line here is model.eval. This officially puts the model into inference mode, turning off dropout and other training-only features. Then we enter a simple while loop that lets us talk to our AI. We get a prompt from the user's input. We use our tokenizer to encode that text into a tensor of token IDs. Then we pass these IDs to our model's generate method, which, as we know, autoregressively predicts new tokens. Finally, we take the list of generated token IDs and use our tokenizer's decode method to turn them back into a human-readable string, and we print it to the screen. This is where we get to see the creativity and knowledge our model has learned from the data. So let's take a moment to appreciate what we've just accomplished. We have built an entire end-to-end language model pipeline from absolute scratch. We created our own tokenizer. We built a data pipeline. We implemented a transformer from its most basic components. We wrote a robust training script with checkpointing and evaluation, and we created an inference script to use our model. You haven't just used an API, you've built the engine behind it. You now have a deep, practical understanding of the technology that is changing the world. I encourage you to take this code, experiment with it, change the configs, train it on your own data, and continue your learning journey. Thank you so much for building this with me today. If you enjoyed this deep dive, please give the video a like, subscribe for more tutorials like this, and let me know in the comments what you're inspired to build next. Happy coding! Hello everyone, and a huge welcome to this coding adventure and BrainOmega channel. Have you ever seen those incredibly realistic AI-generated images and wondered how they're made? It can feel like magic, but today we're going to pull back the curtain and become the magicians ourselves. One of the cornerstone technologies that kicked off the modern generative AI revolution is the Generative Adversarial Network, or GAN. Please note that this is a simplified version of our GAN, which you can access on our GitHub repository. The link is available in the video description. We will also publish an advanced version of the code soon. In this video, we're going to build a complete working GAN from the ground up using PyTorch. We're not just going to import a pre-made model, we are going to write the code for our generator network that creates images and our discriminator network that judges them. We'll watch them compete, learn, and evolve right before our eyes. This is a hands-on journey from a blank script to an AI that can generate handwritten digits that look just like the real thing. It's a foundational project for anyone serious about deep learning. So, grab your favorite drink, open up your code editor, and let's get started. So, what's the big idea behind a GAN? Before we write a single line of code, let's understand the beautiful core concept. The best analogy is to think of a game between an art forger and an art detective. We have two neural networks playing against each other. The first is the generator. This is our art forger. Its goal is to get so good at creating fake art, in our case, images of handwritten digits, that no one can tell it's a fake. It starts out completely clueless, taking a canvas of pure random noise and just splashing paint on it. The second network is the discriminator, our sharp-eyed art detective. Its job is to be an expert critic. It looks at an image and must determine if it's a priceless original from the real museum, our dataset, or a forgery created by our generator. Now here's the adversarial part. We train them together in a loop. The detective gets punished for mislabeling a real image as fake or a fake image as real. The forger gets punished when the detective successfully catches its fakes. So, as the detective gets better, the forger is forced to create more sophisticated fakes to pass inspection. This constant, escalating competition is the engine of learning that pushes our generator to create incredibly realistic images. Alright, let's dive into the code. Before we build our main models, we have two small but very important helper functions. First, let's talk about weights init. A notorious problem with training GANs is that they can be very unstable. Sometimes the generator finds one good image and just keeps making that, or the gradients just vanish. The authors of the DC GAN paper, a landmark in GAN research, discovered that how you initialize the random weights in your neural networks at the very beginning can have a huge impact on training stability. They found that initializing weights from a normal distribution with a mean of 0 and a standard deviation of 0.02 worked really well. This function, weights init, is our tool to apply this specific initialization scheme to all the relevant layers in our models. It's a small trick that can make a big difference. Second, we have our show function. This is purely for us, the humans. Our generator will be producing PyTorch tensors on the GPU with pixel values ranging from -1 to 1. To actually see these as images, we need to do a few things. This function first detaches the tensor from the computation graph and moves it to the CPU because Matplotlib can't work with GPU tensors. Then it reshapes the data and, most importantly, remaps the pixel values from the -1 to 1 range to the 0 to 1 range that image viewers expect. Finally, it arranges them in a nice grid and plots them. This function will be our window into the generator's mind. Next up, let's get our experiment organized with the GAN config data class. When you work on a machine learning project, you'll have dozens of settings: learning rates, batch sizes, image sizes, directory paths, and more. Hard coding these numbers directly into your training script is a recipe for disaster. It becomes messy and impossible to track your experiments. A much cleaner approach is to use a configuration class, and Python's data class is perfect for this. It's like a central control panel for our entire project. We can define all our key parameters right here. For example, S-dimension is the dimensionality of our input noise vector. Think of this as the DNA for each image. A 100-dimensional vector of random numbers is the seed from which an entire image will be grown. lar is our learning rate, and betas are specific parameters for the Adam optimizer that control its momentum. By keeping all these settings in one place, we can easily tweak them, run a new experiment, and see what works best, all without changing our core logic. Now for our first major player, the generator. Remember, this is our art forger. Its mission is to take a simple 100-dimensional random noise vector and transform it into a complex 784-dimensional vector that represents a 28 by 28 pixel image. So, how does it do that? We're using a NN sequential model, which is like an assembly line for data. The noise vector Z goes in one end and the image comes out the other. We're using a series of linear layers to progressively upsample or increase the number of features, from our ZDIM of 100 up to 256, then 512, then 1024, and finally to our target image dimension of 784. After each upsampling layer, we use batch norm 1D. This is a normalization technique that helps stabilize training by keeping the outputs of each layer in a consistent range, which is especially important in GANs. Then, a ReLU activation introduces nonlinearity, allowing the model to learn more complex relationships. The final layer is a tanh activation function. This is a very deliberate choice. Tanh squishes all the output values into a range of -1 to 1. This is crucial because we're going to normalize our real input images to the exact same range. By doing this, we ensure that the fake images created by the generator and the real images from our dataset are on a level playing field. With our forger built, we now need our detective, the discriminator. Its architecture is essentially the mirror image of the generator. Its job is to take a high-dimensional input, a 784-pixel image, and classify it, boiling it all down to a single number representing its verdict, real or fake. It's also an NN sequential model. It takes the flattened image and passes it through linear layers that progressively downsample the number of features, from 512 down to 256. For our activation function, we're using leaky ReLU. This is a popular choice in GAN discriminators. Why? A standard ReLU function outputs 0 for any negative input, which means the neuron can die and stop learning. Leaky ReLU has a small non-zero slope for negative inputs, so it always allows a small gradient to flow through. This helps keep our network alive and learning throughout the training process. Finally, the output layer is a single linear neuron that produces one number, a logit. We don't apply a sigmoid function here because our loss function, BCE with logits loss, is designed to take raw logits for better numerical stability. This single number is the discriminator's final judgment. Okay, our models are designed. Now let's prepare the real art for our detective to study. That's the job of the getDataLoader function. Every image in the MNIST dataset will pass through a small assembly line of transformations we define with transforms compose. First, transforms, resize, make sure every image is the correct size. Then transforms to tensor does two things. It converts the image data into a PyTorch tensor and scales the pixel values from their original range into a new range of 0 to 1. The final transforms normalize 0.5, 0.5 is the key. It takes the 0-1 range and remaps it to 1-1. Why? Because this now perfectly matches the negative 1,1 output range of our generator's TAN activation. This synchronization is critical for fair competition. We then load the MNIST dataset with these transforms and wrap it all in a data loader. The data loader is a fantastic PyTorch utility that automatically handles creating mini batches of data, shuffling the data every epoch to ensure our model doesn't just memorize the order, and using multiple CPU workers to load data in the background so our GPU is never waiting. Alright, it's time to enter the training arena. In the first part of our train function, we do all the setup for the main event. First, we create our output directories and set up a summary writer. This writer is our connection to TensorBoard, a powerful tool that will let us visualize our training progress, like plotting our loss curves in real time. Next, we call our getDataLoader to get our data iterator, and we initialize our generator and discriminator models, making sure to move them to the GPU with .2CFG device if one is available. Then, we immediately call apply weights init on both models. This is where we use our helper function to set their initial weights according to the best practices for GANs. Finally, we set up our criterion, which is BCE with logits loss, the perfect loss function for this kind of binary classification task. And, crucially, we create two separate Adam optimizers. OptGen will only update the weights of the generator, and OptDisk will only update the weights of the discriminator. They are two separate players in this game, so they need their own dedicated optimizers. Now we enter the main training loop, and the adversarial game begins. For every batch of images, round 1 goes to the detective, the discriminator. Our goal here is to make it a better critic. We start by calling optDisk 0grad to clear any old gradients from the previous step. The discriminator's training has two parts. First, we show it the real images. We calculate its loss by comparing its predictions, disk real output, against a tensor of all ones, because we want it to confidently label these as real. Second, we teach it about fakes. We generate a batch of fake images using the generator. Then we pass these fakes to the discriminator. This time we compare its predictions, disk fake output, against a tensor of all zeros. Now look at this line, disk fake detach. The .detach call here is the most critical detail in this step. It tells PyTorch to treat the fake tensor as a constant, as if it were just an image we loaded from a file. This effectively freezes the generator, ensuring that when we call lossDisk.backward, the gradients will only be calculated for the discriminator's weights. We are exclusively training the detective in this round. Finally, we average the loss from the real and fake batches, backpropagate, and update the discriminator's weights. The detective is now a little bit smarter. Okay, the detective has had its turn. Round 2. The forger, our generator, gets to learn. Its goal is simple: to get better at fooling the now smarter discriminator. First, we clear the generator's old gradients with opt Gen 0 grad. Now here comes the beautiful clever trick of GANs. We take the same batch of fake images we created a moment ago and pass them through the discriminator one more time. But notice, this time we do not use dot detach. We want the computational graph to remain connected, so gradients can flow all the way back to the generator. So how do we calculate the generator's loss? We compare the discriminator's output on these fake images to real labels, a tensor of all ones. We are essentially telling the loss function a lie. We are saying the generator's goal is to produce images that the discriminator classifies as real. The loss gene therefore represents how well the generator failed at this goal. By calling loss.gen backward, we calculate the gradients that will teach the generator how to adjust its weights to make its output images even more likely to be classified as real by the discriminator in the future. We then take a step with the generator's optimizer, and the forger's training for this round is complete. Training a GAN without watching it is like flying blind. Is the generator actually improving, or is it just making noise? Is one model overpowering the other? This section of the code is our cockpit dashboard, where we track our progress. Throughout the loop, we accumulate the loss*disk and loss*gen values. Then every log interval steps, we print out the average losses. This gives us a quick numerical check. Ideally, you want to see both losses staying relatively balanced. If one drops to 0, it means one player has completely overpowered the other, and learning has stopped. More importantly, we use torch.nograd. This is a context manager that tells PyTorch, for this block of code, we're just looking, not training, so you don't need to track gradients. This makes everything inside run faster and use less memory. We generate a new sample of fake images and use our show function to plot them next to a batch of real images. This visual feedback is everything. You'll literally see your generator go from producing fuzzy static to recognizable digits over the course of training. Finally, we use our writer to log the scalar loss values to TensorBoard, which will create beautiful graphs for us to analyze later. Finally, let's look at the very bottom of the script. This is standard Python that ensures the code inside only runs when you execute this file directly from the command line, not when it's imported by another file. Here, we're using Python's built-in argparse library. This is what transforms our script into a powerful command line tool. By defining arguments like ~epochs or ~lr, we give ourselves the ability to control our experiments without ever having to edit the source code. This is how you would work in a real research or production environment. You can start one training run with python train.py, epochs 50, and then start another one in a different terminal with python train.py, epochs 100, LR 0.0001 to compare results. The script parses any arguments you provide, uses them to create our GAN config object, and then passes that configuration into our train function to kick off the whole process. It's a very clean and professional way to handle experimentation. So let's take a step back and appreciate what you've just built. This isn't just a script. It's a complete system embodying a fundamental concept in AI. You have built a generator, an AI artist that can create novel content from nothing but random noise. You've built a discriminator, a critical AI judge that learns to differentiate real from fake. And most importantly, you've orchestrated the adversarial training loop, the competitive dance that allows both networks to achieve a state of equilibrium where the generated images become indistinguishable from reality. You've done this all within a clean, configurable project. You now have a deep, hands-on understanding of how GANs work. The next steps are up to you. Try a new dataset like Fashion MNIST. The biggest leap would be to convert our simple linear models into convolutional ones to build a DC GAN, which will yield even more impressive images. But for now, play with the hyperparameters, see what breaks, see what works, and truly make this project your own. Thank you so much for following along with this deep dive. If you found this tutorial helpful, please give it a like and subscribe for more content that goes beyond the surface. Happy generating! Hello everyone, and a huge welcome to this hands-on project. We all know Python is fantastic for getting ideas up and running quickly, but when it comes to raw computational speed, C++ is the undisputed champion. What if we could get the best of both worlds? What if we could write our logic in simple Python and then have a personal AI expert instantly rewrite it into blazingly fast, high-performance C++? You have access to the code on our GitHub page, and you can find the link in the description of this video. Well, today, that's exactly what we're going to build. We are going to create a complete Python to C++ code converter from scratch. This isn't just a simple script, it's a full-stack application that uses powerful large language models like GPT-4o and Claude 3.5 Sonnet as its reasoning engine. We'll build the back-end logic, the AI communication pipeline, and a beautiful web interface with Gradio where you can see the magic happen in real time. This is a deep dive tutorial where we'll explain every line of code and the reasoning behind it. By the end, you'll have a powerful tool and a deep understanding of how to integrate modern AI into your own applications. So, let's get started. Before we write a single line of code, let's zoom out and look at our project's blueprint. A good application has a clear structure, and ours can be thought of as a factory assembly line, with each file playing a specific role. It all begins at the front door, our Gradio user interface, UI.py. This is where the user will interact with our application, pasting in their Python code and clicking buttons. When the user clicks convert, the request is sent to our conversion logic, conversion.py. Think of this as our master translator and project manager. Its job is to take the Python code, wrap it in a carefully constructed set of instructions, and manage communication with our AI models. Next, the conversion logic sends the request over the internet to the LLM API. This is where the heavy lifting happens. A massive model like GPT-4o or Claude analyzes the request and generates the high-performance C++ code. The generated code is then sent back to our application. At this point, our execution engine, execution.py, can be used. This part of our factory is the quality control and testing department. It can compile and run the new C++ code and the original Python code, so we can verify that the logic is correct. Finally, the results, both the newly generated C++ code and the output from execution, are sent back to the Gradio UI to be displayed neatly for the user. Understanding this flow will make it much easier to see how each piece of code we write fits into the bigger picture. Alright, let's start with the foundation of any good project. The configuration file, config.py. Think of this as the central control panel for our entire application. Instead of hard-coding important values throughout our scripts, we define them all in one clean, organized place. First, we use a library called python.env. This allows us to store our secret API keys in a special file named .env. This is a critical security practice because it ensures we never accidentally commit our sensitive credentials to a public GitHub repository. The load.env function reads this file and makes the keys available as environment variables. Next, we create what are called API clients. An API client is an object that handles all the complex details of communicating with a service. Think of it like having a dedicated pre-programmed phone line directly to OpenAI and another one to Anthropic. We instantiate them here so they're ready to use anywhere in our project. We also define our model names as constants. This is great because if a new, better model like GPT-5 comes out, we only have to change the name in this one spot. Finally, we define our system message. This is our prime directive for the AI. It sets the context and personality for every single conversation we have with it. We're telling it from the start. You are an expert C++ developer. Your goal is performance. Your output should be code. This is the foundation of our prompt engineering. Now we move to the heart of our application, conversion.py, and specifically to the most creative part of working with LLMs, prompt engineering. The AI models we're using are incredibly powerful, but they aren't mind readers. The quality of the C++ code we get back is almost entirely dependent on how clearly and effectively we ask for it. Let's break down how we construct our request. The user prompt for function builds the specific task for this one conversion. We don't just give it the Python code. We surround it with very clear instructions. We explicitly say fastest possible implementation and produces identical output. We even give it helpful hints that a good programmer would know, like pay attention to number types to ensure no int overflows, and remember to include all necessary C++ packages. This level of detail dramatically improves the quality of the generated code. Then, the messages for function assembles the final payload. Modern chat-based models work best with a structured conversation history. Here, we create a list of messages. The first message is our system role. Using the system message from our config file, this sets the AI's long-term personality. The second message is the user role, which contains the specific one-time request we just built. This system user structure is the standard and most effective way to guide the model's behavior. With our perfect prompt constructed, it's time to actually send it to the AI. That's the job of our Stream GPT and Stream Claude functions. Now, we could just send the request and wait for the full C++ code to come back, but that might take 5 or 10 seconds, and during that time, our user interface would just be frozen, leaving the user wondering if it's even working. A much better user experience is to stream the response. This means the model sends us the code token by token as it generates it. Let's look at Stream GPT. We make our API call, but we add the crucial argument stream equals true. This changes the return value from a single object to a generator. We can then loop through this generator, and in each iteration, we get a small chunk of the response. We append this chunk to our reply and then yield the current state of the reply. In our UI, this will make the C++ code appear to be typed out in real time. Now, Stream Claude is similar, but adds another layer of professionalism, error handling with exponential backoff. Sometimes a popular API can be temporarily overloaded. This code is wrapped in a try.except block. If it catches an API error that indicates the service is overloaded, it doesn't just crash. It waits for a couple of seconds and then tries again. If it fails again, it doubles the waiting time before the next attempt. This is a robust way to handle temporary network issues and makes our application much more reliable. So we have functions to build our prompt and functions to talk to the APIs. Now we need something to connect them all together. That's the optimize function. It's the orchestrator or the project manager for our backend. This is the single function that our user interface will call. It's very straightforward. It takes the user's Python code and the model they selected from the drop-down menu in the UI. It then uses a simple if-elif block to act as a switchboard, choosing the correct streaming function, Stream GPT or Stream Claude, to call based on the user's choice. It then needs to consume the entire stream. The for loop iterates through every partial result yielded by our streaming function. While the UI will be updating in real time with these partial results, this loop's purpose is to wait until the stream is completely finished and capture the final output. Once the loop is done, we have the complete C++ code. We pass this to our simple write output helper function. This function just does a little bit of text cleaning to remove any markdown formatting the AI might have added, and then saves the final clean code to a file named optimized.cpp. Finally, it returns the complete code, which Gradio will then display in the output text box in our UI. Generating the C++ code is cool, but how do we know it actually works? And is it really faster? That's where our execution.py script comes in. This is our execution engine and testing ground. First, let's look at execute Python. To run Python code that's currently just a string, we can use the built-in exec function. It's very powerful, but be aware, it can be a security risk if you're running untrusted code. To capture the output of any print statements within that code, we do a clever trick. We temporarily hijack Python's standard output and redirect it to an in-memory text buffer using io.stringio. We run the code, capture everything printed to the buffer, and then restore the standard output. Now for execute CPP. This is a two-step process that mimics what a developer would do on the command line. First, we use Python's sub-process module to call the clang ++ compiler. Look at the flags we are using. -std equals C++ 17 ensures we're using a modern C++ standard. Allfast is an aggressive optimization flag telling the compiler prioritize speed above all else. And March native tells it to generate code that is specifically optimized for the exact CPU architecture of the machine it's running on. This is where we get our high performance. If the code compiles successfully, we then use subprocess a second time to run the newly created executable and capture its output. If any errors happen during compilation or runtime, our try except block will catch them and return the error message to the user. Now let's build the front door to our application, the user interface in UI.py. Normally, to build a web interface like this, you'd need to be a web developer and know HTML, CSS, and JavaScript. But the Gradio library is like a superpower for Python developers, letting us build and share interactive UIs with just a few lines of Python. We define our entire layout inside A with GR blocks as UI block. This gives us full control. We use GR tabs to create a clean, organized interface with a conversion tab and an execution tab. Inside these, we lay out our components using GR row and widgets like GR text box for multi-line code input, GR dropdown for our model selection, and GR button for our actions. We can even pass in custom CSS to style it and give it a polished, professional look. Now for the most magical part, the .click methods at the bottom. This is how we wire up our front-end buttons to our back-end Python functions. This one-line convert button.click optimize comma space says everything. When the convert button is clicked, call the optimize function. Take the values from the Python input text box and the model dropdown as its inputs, and whatever that function returns, display it in the CPP output text box. It's an incredibly simple and powerful way to connect a user interface to our code. Last but not least, we have our launcher script, main.py. Every great application needs a single clear starting point, a main entrance, and that's exactly what this file is. Its job is incredibly simple but essential. It imports just one thing, the launch.ui function we just defined in our ui.py file. Then, inside the standard if name equals main block, which ensures this code only runs when we execute this script directly, we do two things. First, we call launch UI, which runs all our Gradio code and constructs the entire UI object in memory. Second, we call the launch method on that UI object. This is the final command that actually starts the local web server, builds the HTML and JavaScript for the web page, and with in-browser equals true, automatically opens a new tab in your default browser pointing to our running application. To start this entire complex full-stack AI application, All a user needs to do is run one simple command in their terminal, python main.py. So let's step back and look at what you have just built. This is so much more than just a simple script. You have orchestrated a complete system of modern AI tools to create a genuinely useful and powerful application. You've learned how to securely manage API keys and interact with state-of-the-art language models like GPT-4.0 and Claude 3.5. You've practiced the crucial art of prompt engineering to guide and control the behavior of these AIs. You've built a robust execution engine that can compile and run native code from Python, and you've wrapped it all in a beautiful full-stack web application using Gradio. The skills you've learned here are the foundation for building the next generation of AI-powered software. I encourage you to take this project and make it your own. Try adding more target languages like Rust or Go. You could even build in an automatic performance benchmark that runs both versions and shows the user exactly how much faster the C++ code is. Thank you so much for joining me on this journey. If you found this tutorial valuable and you feel like you've learned a lot, please give the video a like and subscribe for more deep dives into building real-world AI applications. Happy coding! Hello everyone, and welcome to what I think is a really fun and exciting project. We've all chatted with AI models like ChatGPT or Claude one-on-one, but have you ever wondered what would happen if you put them in the same room and made them talk to each other? What would they say? Would they agree? Would they argue? The complete code of the application is available in our GitHub repository. You can find the link in the description of this video. Well, today we're going to find out. We're going to build a multi-chatbot conversation system from scratch. This application will allow us to give a topic to 3 different AI models, one from OpenAI, one from Anthropic, Claude, and a local Ollama model, and watch in real time as they not only respond to the topic but also critique each other's answers. We'll build the entire system using Python, from the back-end logic that calls the APIs to a beautiful streaming web interface using Gradio. This is a fantastic way to learn about multi-agent systems and API integration. Let's start building our AI debate club. Before we write any code, let's understand the flow of our application. You can think of it as setting up and running a formal debate club. Our Gradio UI, which we'll define in main.py, is where we, the user, act as the moderator. We propose the topic for the debate. When we click Run, the topic is handed off to our conversation conductor, the run conversation function inside conversation.py. This function is like the debate's director. It manages the entire flow. The conductor first sends the initial topic to each of our chatbot agents. Each agent is an instance of our chat system class, which is a universal wrapper we'll build to handle communication with the different APIs. Each agent forms its opening statement. Then comes the most interesting part, the critique round. The conductor takes the response from, say, the OpenAI agent and shows it to the Claude and Ollama agents, asking them, "What do you think of this?" It does this for every agent's response. Crucially, every single message, every opening statement, and every critique is sent back to our Gradio UI the moment it's generated. This is called streaming, and it will allow us to watch the entire debate unfold live. It's a clear, logical flow that we're now going to build piece by piece. Let's start with our most fundamental building block, the chat system class in chatsystem.py. Think of this as a universal translator or a blueprint for any chatbot we want to add to our system. By having this generic wrapper, we can make our project easily extensible in the future. In the init constructor, we store everything that defines one of our debaters. We pass in the processor, which is the actual API client object from libraries like OpenAI or Anthropic. We give it a system string which defines its personality and instructions. We specify the model name, and we initialize an empty list called messages to store this bot's unique conversation history. Now, the call method is where the communication happens. It takes a new message, appends it to its history, and then makes the API call. Here, we see a key piece of real-world coding, handling slight differences between APIs. The Anthropic API for Claude expects the system message to be a separate parameter in the create call. However, the OpenAI API, which the local Ollama server also mimics, expects the system message to be the very first item in the messages list itself. This simple if-else block handles that difference gracefully, allowing our single call method to work for all our bots. Now we move to conversation.py, the script that will direct our AI play. The first part of this file is all about setting the stage and casting our characters. We start by loading our secret API keys from our .env file. Then we initialize the client object for each of our three services. For OpenAI and Claude, it's straightforward. For our local Ollama model, we point the OpenAI client to our local server address, which is typically localhost:11434. Next, we define the specific models we'll be using. I've chosen some fast and capable models here like GPT-4o Mini and Claude 3 Haiku to keep the conversation flowing quickly. And now for the fun part, creating our debaters. We create 3 instances of our chat system class. For each one, we pass in the appropriate client and model name, but most importantly, we give each one a system string that defines its personality. Notice the prompt for OpenAI chat. We've explicitly told it to be insightful but also snarky, to disagree and to challenge everything. This will make the conversation much more interesting. We then group all our chatbot objects into a simple list called chatbots for easy access. This is the core logic of our application, the run conversation function. A key thing to understand is that this is a Python generator function because it uses the yield keyword. Think of yield as pressing a pause button. The function runs until it hits a yield, sends the specified data back to whoever called it, in our case the Gradio UI, and then patiently waits. When the UI is ready for the next update, the function resumes from exactly where it left off. This is the mechanism that enables our real-time streaming display. First, we loop through our chatbots and reset their message history to ensure every conversation starts fresh. We prepare the initial prompt from the user's topic. We set up a dictionary called logs to keep track of the text that will appear in each chatbot's display box. Now, for the first main loop, we iterate through each chatbot in our list. For each one, we first update its log to say calling and immediately yield this status to the UI. Then we make the actual call to the bot's API to get its response to the initial prompt. We store this response and then update the log again with the full response text, yielding once more to the UI. This loop ensures each bot gives its opening statement one by one. Now for the most dynamic part of the debate, the critique round or the rebuttals. This happens right after the first loop finishes. Here we have a nested loop structure. The outer loop iterates through each of our chatbots. This is the bot that will be doing the critiquing. The inner loop then iterates through the responses we collected in the first round. This is the response that is being critiqued. We have a simple if statement to make sure a bot doesn't critique its own response. Then for each critique, we again yield a status update to the UI like critiquing response of Claude. We then construct a brand new prompt. This time, the prompt is very specific. We ask the current bot to critique the following response from, and we insert the other bot's name and its actual response. We then call the bot's API with this new critique prompt to get its analysis. Finally, we format this critique, add it to the bot's log, and yield the final state to the user interface. This nested loop ensures a full round robin of critiques, making for a very interactive and engaging output. Finally, let's look at main.py, where we build the stage for our AI debate using Gradio. This script is wonderfully concise thanks to the power of the Gradio library. We create a layout using GR blocks. We use GR Markdown to add our titles and descriptions. We use GR Row to organize our components horizontally. We create a text box for the user to enter their topic and a button to start the conversation. Below that, we create 3 separate Markdown components, one for each of our AI models, to serve as their display boxes. Now for the most important part, the .click event handler. This single line of code connects our front end to our back end. We tell the run button that when it is clicked, it must call our run conversation function. The input should be the value from our topic input text box. And here's the key for our multi-output display. The outputs parameter is a list of our 3 markdown components. Because our run conversation function yields a tuple of 3 strings, Gradio is smart enough to map the first yielded value to the first output component, the second value to the second, and so on. This is how each bot's log gets routed to the correct box in the UI. Finally, demo.launch starts the web server and opens the application in your browser. So, let's step back and look at the powerful system you've just built. This is more than just a simple chatbot. You've created a universal chatbot wrapper, a piece of reusable code that makes it easy to add new AI models. You've built a multi-agent conductor, a sophisticated piece of logic that can orchestrate complex multi-step interactions between different AIs. And you've wrapped it all in a beautiful streaming web UI that brings the entire process to life. You now have a framework for experimenting with multi-agent AI systems, which is a cutting-edge area of research. The possibilities from here are endless. You could easily add a 4th chatbot to the debate, perhaps one using Google's Gemini API. You could create more complex conversation flows with multiple rounds of rebuttal. You could even change the prompts to make the AIs collaborate on writing a story or solving a coding problem. Thank you so much for following this tutorial. If you learned something new and had fun building this project, please give the video a like and subscribe for more deep dives into creative and practical AI applications. Happy coding! Hello everyone, and welcome to a really exciting and cutting-edge topic in AI. We often think of AI in 2 ways. There's machine learning, which is great at pattern recognition and gut feelings, and then there's old-school symbolic AI, which is based on logic and hard-coded rules. What if we could get the best of both worlds? That's exactly what we're going to do today. We are going to build a neuro-symbolic reinforcement learning agent from scratch. We'll create an agent that learns to solve the classic cart-pole balancing problem using a hybrid brain. One part of its brain will be a fast, dynamic echo state network, providing the neuro component. The other part will be a symbolic reasoning module, a set of human-defined rules that provide the symbolic common sense. We'll code every component, see how they work together, and train the agent to master the game. This is a fantastic look into the future of building more robust and interpretable AI systems. Let's get started. The complete source code for this project is available on our GitHub repository. Just follow the link in the video description to check it out. So, what is the big idea behind our neuro-symbolic agent? We're essentially trying to give our AI 2 different ways of thinking, much like humans do. First, we have our symbolic reasoning module. You can think of this as System 2 thinking. It's slow, deliberate, and based on logical rules that we explicitly write. It's our AI's common sense or rulebook. For the cart pole game, a rule might be as simple as, if the pole is leaning too far to the left, it's a good idea to push the cart to the left. This part of the brain is easy for us to understand and debug, but it might not be able to handle every complex situation. Second, we have the Echo State Network, or ESN. This is our System 1 thinking. It's fast, intuitive, and based on recognizing complex patterns over time. It's a special kind of recurrent neural network that maintains a rich, echoing memory of recent events. It doesn't operate on explicit rules. It just develops a gut feeling about the state of the game. Our agent's strategy is to listen to both its logical rulebook and its neural intuition, combine their advice, and then make a final, more robust decision on which action to take. Let's start with the most straightforward part of our hybrid brain, the symbolic reasoning module. This class is our explicit rulebook. In the init method, we define a dictionary called rules. Each key corresponds to a piece of the game's state, like pole angle, and its value is a lambda function that represents our rule. For example, the pole angle rule says, if the angle is very negative, leaning left, strongly suggest moving left by outputting 0.9, 0.1. If it's very positive, leaning right, strongly suggest moving right with 0.1, 0.9. Otherwise, if it's balanced, have no opinion and output 0.5, 0.5. We have a similar rule for the cart's position. The forward method takes the current state of the game, extracts the relevant values, applies all the rules, and then simply averages their suggested action probabilities to get a final symbolic output. We also have a refine rules method, which is a very simple way to make our symbolic system adaptable. After an episode, if the overall feedback was negative, it will update the rules to be a little less confident in their suggestions. It's a basic form of learning for our logical system. Now for the neuro part of our agent, the Neuro-Symbolic Echo State Network. Let's really take our time here and focus on how we initialize its core component, the reservoir, because this is what makes an echo state network so unique and powerful. An ESN is a type of recurrent neural network, but it has a revolutionary twist. In a traditional RNN, you use backpropagation to painstakingly train all the weights, which can be slow and difficult. The incredible idea behind ESNs is that we can create a large, complex, randomly generated network and keep its internal connections fixed. We never train them. This fixed network is called the reservoir. Think of it like a complex wind chime. You don't train the wind chime, you just build it. But when a gust of wind, our input signal, blows through it, the chime produces a very rich and complex set of sounds or echoes that are a high-dimensional representation of that simple gust. The reservoir works the same way. It's an echo chamber for data. When we feed our game state into it, the signal bounces around this fixed, random structure, creating complex patterns and dynamic states that capture the history of what has happened. So, how do we build this? First, we create self, win. This is the input weight matrix. It's our door into the reservoir. Its job is to take the low-dimensional game state, which has 4 features, and project it into our much higher dimensional reservoir space, which has 150 features. We initialize it with small random numbers. Next, and this is the most important part, we create self-W, the recurrent weight matrix that defines the internal connections of the reservoir itself. This is a careful 4-step process. We start with a dense matrix of random numbers using NumPy. We introduce sparsity. We create another random matrix of the same size and use it as a mask to set about 90% of the connections in W to 0. Why do this? A sparse reservoir is often more stable, computationally cheaper, and can lead to richer, more decoupled dynamics. Now for the magic, spectral radius scaling. This is a crucial mathematical step to ensure the reservoir has the echo state property. We calculate the eigenvalues of our matrix W and find the one with the largest absolute value. This is the spectral radius. We then scale our entire W matrix by this value. This ensures that the reservoir is stable. It prevents the echoes from either dying out to 0 instantly or exploding into infinity. We scale it by a factor of 0.9 to keep it just on the edge of stability, which is often where the most interesting dynamics occur. Finally, we convert our NumPy matrix W into a PyTorch tensor. Notice very carefully that we are not wrapping it in nen.parameter. This is how we tell PyTorch that these weights are fixed and should not be updated during training. This is the defining characteristic of an echo state network and what makes it so efficient. Continuing in our init method, let's assemble the rest of our hybrid model. After creating our input and reservoir weights, we initialize self.state, which is a vector of zeros that will hold the activation values of our reservoir neurons at each time step. Next, we create an instance of our symbolic reasoning module, the rulebook we defined earlier. This means every instance of our ESN will contain its own little logical component. Now for the most important part of an echo state network, the readout layer. This is a simple NN linear layer. The revolutionary idea of ESNs is that the randomly initialized reservoir is powerful enough to generate useful features. So the only part we actually need to train is this final readout layer. It reads the state of the reservoir and learns to map those complex patterns to a useful output. But look at its input dimension, reservoir dimension plus symbolic dimension. Our readout layer isn't just looking at the neural reservoir, it's also looking at the output from our symbolic module. This is the point of fusion where our two ways of thinking, the neural and the symbolic, come together before a final decision is made. Now, let's trace the flow of data through our model in the forward pass. This is what happens every time our agent needs to decide on an action. First, we update the state of our reservoir. The new state is calculated by taking the current input x multiplied by the input weights, adding it to the previous state of the reservoir multiplied by the recurrent weights, and then passing the result through a tanh activation function. This is what makes it a recurrence network. Its current state depends on its previous state. This is our neurosignal. Second, in parallel, we call the forward method of our symbolic module. This takes the same input x and uses our hard-coded rules to produce the symbolic signal. Third, we combine these two signals. We use TorchCat to simply concatenate the reservoir state vector and the symbolic output vector into one larger vector. Finally, this combined vector, which now contains both the intuitive patterns from the ESN and the logical suggestions from the rulebook, is passed to our single trainable readout layer, which produces the final output scores for each possible action. The output of our Neuro-Symbolic echo state network is a set of raw scores, or logits, for each action. To use this in our reinforcement learning context, we need to convert these scores into probabilities. That's the simple job of our policy network class. It's a very thin wrapper. In its init method, it takes our ESN model as an argument and also defines a softmax layer. In its forward method, it first calls our ESN to get the raw scores. Then, it passes those scores through the softmax layer. Softmax is a mathematical function that takes a vector of numbers and turns it into a probability distribution, a new vector where all the elements are between 0 and 1 and they all sum up to 1. The output of this policy network is what we'll use to actually choose an action. All right, it's time to bring everything together in our main train function. This is where we set up the entire reinforcement learning experiment. First, we set our device to a GPU if one is available, and we create our CardPole v1 environment using the gym library. We then get the input.dim and action.dim directly from the environment itself. This makes our code flexible. We also choose the size of our ESN's reservoir. This is a key hyperparameter we could tune later. Next, we instantiate our models. We first create the Neuro-Symbolic echo state network, and then we wrap it inside our policy network. Finally, we set up our optimizer. We're using the popular Adam optimizer. Now look closely at what we pass it. Policy.parameters. This is a key detail of using an echo state network. Because we defined the reservoir weights self.w as simple tensors and not nn.parameters, they are not included in this list. The only trainable parameters here are from the ESN's readout layer and the softmax layer. This is why ESNs can be so fast. We are only optimizing a very small part of the network. Now we enter the main training loop, which runs for a set number of episodes. Each episode is like one full attempt or one life for our agent. Inside the while not done loop, our agent interacts with the world. At each time step, first, it takes the current state and passes it to our policy network to get a vector of action probabilities. Second, instead of just greedily picking the action with the highest probability, we create a categorical distribution and sample from it. This sampling introduces exploration, allowing the agent to try out different actions and discover what works best. Third, we store the log probability of the action we just sampled. This is crucial for the policy gradient calculation we'll do later. Fourth, we perform the action in the environment using env step. The environment responds with the next observation, a reward, and flags to tell us if the episode has terminated. Finally, we store the reward we received and update our state to be the next state we just observed, getting ready for the next iteration of the loop. This slide shows the part of the code where our hybrid neuro-symbolic approach really comes to life. Inside the step loop, after our agent acts and receives a reward, we update a feedback dictionary. This is separate from the main reinforcement learning process. We're essentially creating a simple credit assignment system for our rules. For instance, for the pole angle, we check if the pole is nicely centered. If it is, we add the positive reward to its feedback score. If it's tilted too far, we give it a penalty of -1, regardless of the reward from the environment. We do the same for the cart's position. This helps us track if the states where our rules are active are generally leading to good or bad outcomes. Then, crucially, after the entire episode is finished, we call esn.refine symbolic rules and pass in this accumulated feedback dictionary. This is where our symbolic module gets a chance to learn and adapt its own rules based on the overall performance during that episode, making our entire system more adaptive. After each episode concludes, our agent needs to reflect on what happened and learn from its experience. This is done using the reinforced policy gradient algorithm. First, we need to figure out how good each action really was. Instead of just using the immediate reward, we calculate the discounted return. We loop through the rewards backwards, and for each step, we calculate R, which is the immediate reward plus the discounted value of all future rewards. This gives us a better estimate of the long-term value of being in a particular state. Second, we standardize these returns by subtracting the mean and dividing by the standard deviation. This is a very common and effective trick in policy gradient methods that helps stabilize training. Third, we calculate our loss. The formula is simple but powerful. For each action taken, we multiply its log probability by the standardized discounted return we just calculated. The intuition is this: if an action led to a high positive return, we want to make that action more likely in the future. If it led to a low negative return, we want to make it less likely. Finally, we perform the standard PyTorch update steps. We zero the gradients, backpropagate our calculated loss, and take a step with our optimizer. This updates the trainable weights in our ESN's readout layer, making our policy smarter for the next episode. So, let's step back and look at the amazing hybrid AI we've built today. This is not a standard black box neural network. We created a symbolic module, a transparent rulebook that injects our own domain knowledge into the agent. We also built an echo-state network, a fascinating type of recurrent network that uses a fixed reservoir to efficiently capture temporal patterns. We then fused these two components into a single neuro-symbolic model, creating an agent that benefits from both logic and intuition. Finally, we successfully trained this hybrid brain using the classic reinforce algorithm to solve the cart pole challenge. This project is a fantastic starting point into the world of neuro-symbolic AI. From here, you could try designing more complex and adaptive symbolic rules. You could swap out the echo state network for other popular architectures like an LSTM or even a small transformer. Or you could try applying this powerful hybrid approach to much more complex reinforcement learning problems. Thank you so much for joining me on this deep dive. If you enjoyed building this and learned something new, please give the video a like and subscribe for more tutorials on cutting-edge AI concepts. Happy coding! Hello everyone, and welcome to a deep dive tutorial on a truly fascinating and powerful corner of the neural network universe: echo state networks. If you've worked with recurrent neural networks like LSTMs or GRUs, you know how powerful they are, but you also know that training them can be incredibly slow and computationally expensive. Today we're going to explore an alternative paradigm called reservoir computing, and specifically its most popular implementation, the echo state network or ESN. We're going to learn the theory behind why these networks are so efficient, and then we're going to build one from absolute scratch. But we won't stop there. We'll build an advanced multi-scale ESN and use it as the brain for a reinforcement learning agent tasked with solving the classic cart pole problem. This is a university-level topic, but we're going to break it down step by step so that every component is crystal clear. This will be a long and detailed session, so get comfortable and let's begin our deep dive. You can find the complete project code on our GitHub. Just click the link in the description below this video. Before we dive into our solution, the echo state network, let's first understand the problem it was designed to solve. Why do we need an alternative to standard recurrent neural networks like LSTMs or GRUs? While these traditional RNNs are incredibly powerful for processing sequential data, they come with some significant challenges, especially during training. The main training algorithm, backpropagation through time, involves unrolling the network through its history, which is a very slow and memory-hungry process. Furthermore, they suffer from the infamous vanishing and exploding gradients problem. Imagine you're trying to teach the network by sending an error signal backwards in time. As this signal travels, it's repeatedly multiplied by the network's weights. If those weights are small, the signal can shrink exponentially until it vanishes, and the network can't learn from events that happened long ago. If the weights are large, the signal can explode, destabilizing the entire training process. This leads to a difficult and often frustrating process of hyperparameter tuning to get them to work well. This begs the question that researchers asked in the early 2000s: can we get all the benefits of these rich recurrent dynamics without paying the high price of this complex training? The answer, it turns out, is yes. This brings us to the beautiful and elegant core idea of the echo state network. The key insight is to decouple the part of the network that creates rich dynamics from the part that actually learns. An ESN consists of three distinct parts. We have an input layer, which simply feeds our external signal into the system. Then we have the heart of the ESN, the reservoir. This is a large, recurrently connected network of neurons. But here's the radical idea. We initialize this reservoir with random weights, and then we freeze it. We never ever train or update these internal connections. Its sole purpose is to act as a high-dimensional, nonlinear echo chamber. When an input signal enters, it causes complex reverberations or echoes throughout this reservoir. The state of the reservoir at any moment is a rich, dynamic reflection of the recent history of the inputs it has seen. Finally, we have the readout layer. This is a very simple linear layer, and it's the only part of the entire system that we train. Its job is to look at the incredibly complex and high-dimensional state of the reservoir's neurons and learn to map that state to our desired output. The best analogy is to imagine throwing a stone, which is our input, into a pond, which is our reservoir. The pond's physics are fixed. You don't train the water. But by observing the complex pattern of ripples on the surface, you can learn to infer what kind of stone was thrown and when. In an ESN, we don't train the reservoir. We only train the readout layer to learn how to interpret the ripples. Before we dive into the code for a single echo state network, let's first understand the powerful, high-level architecture we'll be using in this project, the multi-scale echo state network. So why would we need more than one reservoir? Think about how you perceive the world. To make a good decision, you need to process information at different speeds or timescales. For the cart pole problem, the agent needs to react to very fast changes, like a sudden wobble of the pole. But it also needs to be aware of slower moving trends, like the cart consistently drifting too far to one side of the track. A single reservoir might be good at one of these, but not the other. A multi-scale ESN solves this by creating a team of specialists. Instead of one giant reservoir, we create several smaller independent reservoirs. Each reservoir in our team is configured with different properties, allowing it to specialize in capturing dynamics at a specific timescale. Let's look at the parameters we'll use in our code to define this team. First, reservoir dimensions. We are creating 3 reservoirs and we are giving them different sizes, 300, 400, and 500 neurons. Giving them different sizes can provide varying levels of complexity and capacity for the patterns they can represent. Next, spectral radii and sparsities. For this particular experiment, we're keeping these consistent across all 3 reservoirs to isolate the effect of the other parameters. They are all set to stable, well-established values. Now, for the most important parameter in our multi-scale design, leaky rates. This is how we create our specialists. We're giving each reservoir a different leaky rate, 0.2, 0.3, and 0.4. The reservoir with a high leaky rate of 0.4 will be our short-term memory expert. Its internal state will be heavily influenced by the most recent input, making it highly reactive and great at capturing fast-changing details. The reservoir with a low leaky rate will be our long-term strategist. Its neurons are more stubborn. They hold on to their previous state more strongly. This allows it to smooth out noisy inputs and integrate information over a much longer period, helping it recognize slow-moving trends. The one in the middle, at 0.3, provides a balanced perspective. The final step is to take the rich state vectors from all 3 of these specialist reservoirs and simply concatenate them together into one large superstate vector. This combined vector is then fed to our single trainable readout layer. By doing this, we are giving our decision maker the richest possible view of the world. It gets to hear from the short-term specialist, the long-term strategist, and the balanced expert all at once before making its final move. All right, let's dive into the code and build our echo state network class piece by piece. We'll start with the constructor, the init method. The first thing we do after calling super.init and storing some hyperparameters is to create our input weights, which we'll call win. This is the first component from our diagram. Its job is to take the input vector, which for cart pole has a dimension of 4, and project it into the much higher dimensional space of our reservoir, which might have 300, 400, or 500 neurons. We initialize this weight matrix with random values drawn from a uniform distribution. The torch.rand gives us values between 0 and 1, subtracting 0.5 centers them around 0, and multiplying by 2 scales them to be between -1 and 1. This is a standard way to create initial random weights. Now notice this line, self-register buffer. This is very important. In PyTorch, a parameter is a tensor that the optimizer knows it needs to update during training. A buffer, on the other hand, is a tensor that is part of the model state but is not considered a trainable parameter. By registering W in as a buffer, we are telling PyTorch, this is part of my model, so please move it to the GPU along with everything else, but do not try to calculate gradients for it. This is central to the ESN philosophy of keeping the input and reservoir connections fixed. Okay, we have our input weights. Now for the most interesting part, creating the recurrent reservoir weights, W. This matrix defines how the neurons inside our reservoir are connected to each other. The first step is to introduce sparsity. Why do we do this? A fully connected recurrent network can sometimes have dynamics that are too rigid or chaotic. By making the network sparse, meaning most neurons are not connected to most other neurons, we can encourage richer and more stable patterns to form. It's like having many smaller independent pathways for information to flow and interact. So, how do we do it in code? It's a simple three-step process. First, we create a dense square matrix W of the desired reservoir size with random values centered around 0. Second, we create a Boolean mask of the exact same size. We generate another matrix of random numbers between 0 and 1, and we check where these numbers are greater than our sparsity hyperparameter. So if sparsity is 0.5, this mask will be true for roughly half of its elements. Third, we use this mask to index into our weight matrix W and set those elements to 0. We've effectively just pruned a huge number of connections, leaving us with a sparse, random, recurrent network. The next crucial step is to make sure this network is stable. This next piece of code is the most mathematically important part of creating our ESN. It's called spectral radius scaling, and its job is to ensure our reservoir has the echo state property. In simple terms, this property means that the influence of a past input should gradually fade away over time, but not too quickly. If the echoes die too fast, the network has no memory. If the echoes explode and become chaotic, the network state is useless. We need to find that perfect balance. The key to this balance is the spectral radius of our weight matrix W, which is defined as its largest absolute eigenvalue. For a stable system, this value needs to be less than 1. So our goal is to take our random sparse matrix W and scale it down so that its spectral radius is exactly equal to our desired value spectral radius hyperparameter, which is typically a value like 0.9. Calculating the exact eigenvalues is slow, so instead we use a fast and effective approximation method called power iteration. We start with a random vector EIG. Then we repeatedly multiply our matrix W by this vector. At each step, the vector EIG gets more and more aligned with the principal eigenvector of W. We normalize it at each step to prevent its magnitude from exploding. After about 50 iterations, the norm or length of this vector becomes a very good approximation of the largest eigenvalue. Once we have this maxig, the final step is simple. We just scale our entire weight matrix W by our target spectral radius divided by the max EIG we just found. This guarantees that our new scaled W has exactly the spectral radius we want, ensuring our reservoir is stable and ready to produce useful echoes. We then register this final W as a buffer. Now that we've meticulously constructed our ESN in the init method, let's look at the forward pass. This is what happens at every single time step of the simulation. First, we make sure our input x is a flat vector. Then we come to the single most important equation in our network, the state update equation. This is what makes it a leaky integrating ESN. Let's break it down. The torch.tanh part is the standard RNN update. We take the current input x multiplied by the input weights, add it to the previous reservoir state, multiplied by the recurrent weights, and pass it through a tanh activation. This gives us the new potential state, but we don't just replace the old state with the new one. Instead, we perform a weighted average. We take 1 minus leaky rate times the old state and add leaky rate times the new potential state. The leaky rate is a hyperparameter that controls how fast the reservoir state changes. A small leaky rate means the neurons are stubborn and hold on to their old state for longer, giving the network a longer memory. A large leaky rate makes the neurons update more quickly in response to new inputs. Finally, we normalize the resulting state vector by its norm. This is an extra trick to ensure the activations don't grow too large over time, which further improves the stability of our system. The output of this module is not a prediction, but the rich, high-dimensional state of the reservoir itself. Now, let's see how simple the code for the multiscale ESN is now that we've done all the hard work in our base EcoState network class. This multiscale ESN class is essentially a manager for our team of reservoirs. In the init method, instead of single hyperparameters, it takes lists. A list of reservoir, DIMs, spectral, radii, sparsities, and leaky rates. It then uses a list comprehension to create multiple EcoState network instances, one for each set of parameters, and stores them in an NN module list. Then it creates our single trainable readout layer. Notice its input size, sum of reservoir dimensions. If we have reservoirs of size 300, 400, and 500, the input to this readout layer will be 1200. It's going to see the combined state of every reservoir simultaneously. The forward pass is just as elegant. It passes the input X to each reservoir in the list, collecting their individual state vectors. It then uses torch cat to concatenate these state vectors into one single large superstate vector. This combined vector, which contains information at multiple timescales, is then passed to our trainable readout layer to produce the final output scores. With our complex multiscale ESN brain fully designed, the rest of the setup is standard reinforcement learning practice. First, we have the policy network class. This is an extremely simple but necessary wrapper. Its only job is to take the raw output scores or logits from our ESN and pass them through a softmax function. This converts the scores into a valid probability distribution where each value is between 0 and 1 and they all sum to 1. This gives us the probability of taking each possible action. Now, in our train function, we begin by setting up our experiment. We create our cart pole environment. We then define the lists of hyperparameters for our 3 different reservoirs. Notice that the leaky rates are different, 0.2, 0.3, and 0.4. This is how we're creating reservoirs that capture information at different timescales. We then instantiate our multi-scale ESN with these parameters and wrap it inside our policy network. Finally, we create our Atom optimizer. And again, it's crucial to remember that when we call policy.parameters, the only trainable weights it will find are those in the single readout layer of our multi-scale ESN. The vast majority of our network's parameters are fixed, which is why this approach is so efficient. Now we're inside the main training for loop, which iterates through episodes. Each episode is one full attempt by our agent to balance the pole. Inside the while not done loop, the agent lives its life step by step until the pole falls over. At each step, it performs a sequence of actions. First, it passes the current state of the environment to our policy network to get action probabilities. Second, it creates a categorical probability distribution from these probabilities and samples an action. This is a key concept in policy-based reinforcement learning. Instead of always choosing the action with the highest probability, which would be exploiting its current knowledge, sampling allows the agent to explore by occasionally trying out less likely actions. This is how it discovers new and better strategies. Third, we calculate and store the log prob or log probability of the action we just chose. We need this later for the policy gradient update. Fourth, we execute that action in the environment, and it gives us back the next state, the reward for that step, and whether the episode is done. Finally, we store the reward we received in our rewards list and update our state variable for the next iteration of the loop. We're essentially just collecting data during this phase, a history of actions taken, their log probabilities, and the rewards received. Once the episode is over, it's time for our agent to learn. We use a classic policy gradient algorithm called reinforce. The first thing we need to do is figure out how good each step of the episode actually was. Just looking at the immediate reward of +1 isn't enough. We want to know which actions led to long-term success. To do this, we calculate the discounted return for each step. We loop through the rewards list backwards. For each step, we define its return R as its immediate reward R plus gamma times the return of the next step. This gamma is a discount factor, usually around 0.99, which makes future rewards slightly less valuable than immediate ones. This process gives us a much better estimate of the true long-term value of each action we took. Next, we standardize these returns by subtracting their mean and dividing by their standard deviation. This is a crucial trick that helps stabilize training by keeping the values in a predictable range. Now we calculate our loss. The formula is the heart of the reinforce algorithm. For each step, we take the log prob of the action we took and multiply it by the standardized return for that step. The negative sign is there because optimizers work by minimizing loss. By minimizing this value, we are effectively pushing up the probability of actions that led to high returns and pushing down the probability of actions that led to low returns. Finally, we perform our standard PyTorch optimization. We zero the gradients, backpropagate our loss, and step the optimizer. This sends the learning signal back and updates the only trainable part of our model, the readout layer. So let's take a moment to recap the advanced and fascinating system we've built today. We didn't just build a neural network. We built an echo-state network from the ground up. We went through the detailed theory and code for creating a sparse, random reservoir and ensuring its stability through spectral radius scaling. We then took it a step further, creating a multi-scale architecture by combining a team of ESNs, each tuned to a different time scale using a different leaky rate. This allowed our agent to process both long-term trends and short-term events simultaneously. We embedded this complex brain into a reinforcement learning agent and successfully trained it using the reinforced policy gradient algorithm, teaching its simple readout layer how to interpret the rich dynamics of the reservoirs to solve the cart pole problem. The result is a highly efficient recurrent model that demonstrates a powerful alternative to traditional RNNs. I highly encourage you to take this code and experiment. See for yourself how changing the reservoir sizes or the leaky rates affects the agent's learning speed and final performance. Try applying this architecture to a more challenging environment. This is a fantastic foundation for exploring the world of reservoir computing. Thank you so much for joining me for this deep dive. If you enjoyed it and learned something valuable, please give the video a like and subscribe for more advanced AI tutorials. Happy coding! Welcome to the BrainOmega channel. In today's session, we're diving into a crucial topic in the world of artificial intelligence. The main goal of this tutorial is to take a significant step forward toward understanding and implementing LLM alignment within our community. So what exactly do we mean when we talk about alignment in large language models? At its core, alignment isn't just about making an AI smarter, it's about making it wiser and more responsible. As you can see on the slide, alignment is the dedicated process of training and fine-tuning an LLM so that its actions and responses are consistently in sync with human values and intentions. The ultimate objective is to sculpt these powerful models into partners that are not only helpful but also fundamentally safe to interact with. The diagram on the right beautifully illustrates this. It's a continuous cycle. We provide feedback, which helps refine the large language model. This refinement leads to what we call aligned positive outcomes, outputs that are beneficial and in line with our expectations. This process is repeated, creating a constant loop of improvement. To achieve this, the entire concept of alignment is built upon three foundational pillars: being helpful, honest, and harmless. First, helpful. This means the AI must go beyond just processing words. It needs to accurately grasp the user's true goal and genuinely attempt to meet that need. It's about being a useful and effective tool. Second, honest. An aligned LLM must be a source of truth. It should provide factually correct information and crucially have the integrity to admit when it doesn't know something, rather than fabricating an answer. This pillar is all about building trust. And third, harmless. This is the ethical safeguard. The model must be explicitly designed to steer clear of generating content that is dangerous, biased, unethical, or otherwise harmful. It's our commitment to ensuring AI contributes positively to the world. By focusing on these three pillars, we can guide the development of large language models that are not just powerful, but also principled and beneficial for everyone. For those of you who want to dive deeper, the source code of this tutorial and the project is accessible in our GitHub repository. You can have access to the link in the description of this video. Now that we understand what alignment is, let's explore what it gives us and what its limitations are. This slide tackles a crucial distinction. Alignment is a powerful path toward building trust in AI, but it's not a magic bullet for achieving full explainability. First, let's focus on the strong link between alignment and trustworthiness. Think about anyone or anything you trust in your daily life, perhaps a skilled pilot or a seasoned doctor. You trust them because their actions are reliable, predictable, and consistently lead to positive outcomes. It's the exact same principle with LLMs. By meticulously aligning a model to be helpful, honest, and harmless, we ensure its behavior is consistent and acts in the user's best interest. As the Venn diagram illustrates, an aligned LLM and a trustworthy LLM are deeply interconnected concepts. Alignment is the how, trustworthiness is the result. However, the story changes when we compare alignment to explainability. Here, the link is much weaker, and this is a critical concept to grasp. Alignment is primarily concerned with the output, the what. It asks, is the model's final answer correct, safe, and useful? We are validating the quality and safety of the end product. Explainability, on the other hand, digs into the process, the why. It seeks to answer how exactly did the model navigate its billions of parameters to generate that specific output. This brings us to the black box dilemma, perfectly shown in the second diagram. We can have a model that is perfectly aligned. It gives us a validated, correct, and safe output every time. Yet the internal decision-making process that produced it can remain opaque. We can confirm what it concluded, but we can't always trace the precise path of why. So, the key takeaway is this. Alignment is our most effective tool for creating reliable, predictable, and safe AI that we can fundamentally trust. It solves the problem of behavior. But we should see it as distinct from the separate, ongoing scientific challenge of making these incredibly complex systems completely transparent. So, where is the field of alignment heading? This slide gives us a glimpse into the future, moving beyond the basics to explore the core philosophies and advanced techniques that are defining the next generation of AI. As the diagram illustrates, the path forward involves integrating three powerful and sophisticated approaches to build a more deeply and reliably aligned AI. Let's look at each of these pillars. First, we have AI-driven preference labeling. One of the biggest challenges in alignment is the sheer scale of human feedback required. It's incredibly time-consuming and costly. This technique is the solution. We are essentially training one AI model to understand human values and preferences so well that it can automate the process of labeling data for other models. Think of it as creating an AI supervisor that can apply human-like judgment at machine speed, breaking the bottleneck of manual work. Next, we have constitutional methods. This is a profound shift in philosophy. Instead of just telling an AI what not to do from the outside, we embed a set of core principles, a constitution, directly within its own operational logic. This gives the AI a framework for self-correction. It can review its own response, check it against principles like be helpful and harmless, and then revise it before it ever reaches the user. It's about building models with an internal moral compass. Finally, let's talk about advanced reasoning curricula. This is about teaching an AI how to think, not just what to know. Rather than just exposing a model to vast amounts of data, we create a structured training program, much like a school curriculum for a person. This curriculum is specifically designed to enhance the AI's ability to perform complex, multi-step reasoning and to follow a logical chain of thought. It's the difference between memorizing facts and developing true critical thinking skills. Ultimately, these three frontiers are converging. By automating feedback at scale, instilling principles for self-governance, and actively teaching complex reasoning, we are building the foundation for AI that is more capable, robust, and fundamentally aligned with human values. So, how do we actually implement alignment? Let's dive into the most common and effective method used today, RLHF, which stands for Reinforcement Learning from Human Feedback. As the diagram here illustrates, it's a dynamic, multi-stage process that creates a powerful feedback loop between human trainers and the AI model. The entire process begins with Step 1, Supervised Fine-Tuning or SFT. Think of this as the model's foundational education. We take a massive pre-trained model and give it its first taste of what we want it to be. We do this by training it on a high-quality human-crafted data set of ideal conversations. This is like giving a student a textbook filled with perfect examples to learn from. This initial step teaches the model the basic style, tone, and safety protocols we expect. Step 2 is about building a judge. This is where we train the reward model. We take our model from the first step and have it generate several different responses to a variety of prompts. Then, human reviewers look at these responses and rank them from best to worst. This data, this collection of human preferences, is then used to train a completely separate model. The sole purpose of this reward model is to learn to predict which kinds of answers humans will prefer. It becomes an automated judge of quality. Finally, we reach Step 3, Reinforcement Learning Optimization. This is the most dynamic phase. The main LLM now operates in a live training environment. It generates a response, and our reward model, the AI judge we just built, immediately gives that response a score. This score acts as a reward signal in a reinforcement learning loop. Using a common algorithm like PPO, the model continuously adjusts its own internal strategy to try and maximize the rewards it gets from the judge. It's essentially a cycle of trial and error at a massive scale, where the model learns to consistently produce outputs that it knows will be scored highly by the human-calibrated reward model. So, in short, we first show it what good looks like, then we build a judge that understands our preferences, and finally, the model practices in front of that judge to perfect its behavior. This sophisticated three-step process is the engine behind today's most capable and aligned LLMs. Imagine you're a music producer trying to get the perfect vocal take. The old way is complicated. You first hire a panel of music critics to write a detailed scoring rubric for what good singing is. Then you use that complex rubric to coach the singer, take by take. It's slow, expensive, and often unstable. What if you could just sit with the singer, play them two different melodies, and say, I prefer this one? You just provide a simple preference. The singer learns directly from your choice, gradually steering their performance toward what you like. That, in a nutshell, is the breakthrough of direct preference optimization, or DPO. It's a powerful and elegant technique that scraps the complex machinery of traditional methods and teaches language models to be more helpful, safe, and aligned directly from simple human or AI feedback. Before DPO, the gold standard was reinforcement learning from human feedback, or RLHF. As the name suggests, it's a multi-stage process. First, you train a separate reward model. You show it thousands of pairs of model responses and ask humans which one they prefer. The reward model learns to predict which response will get a higher score. Second, you use that reward model as a judge in a complex reinforcement learning loop. Your language model generates text, the reward model scores it, and you use algorithms like PPO to nudge the language model's policy toward generating higher scoring text. This process works, but it's a beast to manage. It involves training two massive models. It's computationally expensive because you're constantly sampling from the policy, and it's notoriously unstable and sensitive to hyperparameters. DPO's authors asked a brilliant question. Can we skip the separate reward model and the RL loop entirely? Their key insight was this: your language model is secretly a reward model. Through a clever mathematical derivation, they showed that any optimal policy trained with RLHF has a direct fixed relationship with its underlying reward function. This means you can rephrase the entire optimization problem. Instead of training a reward model and then training a policy to match it, DPO defines the loss directly in terms of the policy itself. It collapses two complex stages into one simple, stable step. So, how does it do this? Let's look at the DPO loss function. It might look intimidating, but the idea is incredibly intuitive. For every training example, you have a prompt, a preferred response, Y sub W, and a rejected response, Y sub L. The DPO objective is to maximize the likelihood of the preferred responses over the rejected ones. Let's break it down. The core idea. At its heart, it looks at the log probabilities your model, pi theta, assigns to the winning and losing responses. The goal is to make the winner's probability go up and the loser's go down. The reference model, pi ref. You don't want the model to stray too far from its original stable knowledge base. The reference model, usually your initial supervised fine-tuned SFT model, acts as an anchor. DPO penalizes the policy for deviating too much from this reference, which prevents the model from forgetting its core capabilities or collapsing into repetitive outputs. The beta hyperparameter. This is your main tuning knob. It controls the strength of that anchor. A low beta keeps the model very close to the reference policy, leading to more conservative updates. A high beta allows the model to chase the preferences more aggressively, but risks instability. Think of it as the stretchiness of a leash. The sigmoid weight. This is the most elegant part. The entire term is wrapped in a logistic sigmoid function. This acts as a dynamic, intelligent weight. When the model already assigns a much higher probability to the winning response than the losing one, this weight is small. But when the model is wrong, when it thinks the losing response is better, the weight becomes large. This forces the model to focus its learning effort on the examples it's getting wrong, making training incredibly efficient and stable. In short, DPO increases the relative log probability of preferred responses, weighted by how incorrectly the model currently ranks them. The beauty of DPO is its simplicity. The practical pipeline is just 2 steps. Data collection: start with a supervised fine-tuned SFT model. For a set of prompts, generate 2 responses. Have a human labeler or a more powerful AI. Choose the preferred one. This creates your preference dataset. If you're using a public dataset, this is already done for you. Fine-tuning: optimize your SFT model using the DPO loss function. That's it. No separate reward model, no complex RL sampling loops. The paper even provides a PyTorch implementation that's just a handful of lines long. And if you don't have an SFT model to start with, the paper suggests a simple hack. Just fine-tune a base model on only the winning responses from your preference dataset to create a proxy SFT model before you begin DPO. So, does it work? The paper's experiments show a resounding yes. More efficient. On a controlled sentiment generation task, DPO achieved a better reward KL trade-off than PPO, even when PPO had access to the true ground truth reward function. This means for any given level of deviation from the original model, DPO gets you a higher reward. Higher quality. In summarization and single-turn dialogue, DPO consistently matched or outperformed strong RLHF baselines. For instance, in summarization, DPO achieved a 61% win rate against reference summaries, beating PPO's best performance of 57%. It was also the only computationally feasible method that significantly improved upon the chosen responses in the Anthropic dialogue dataset. More stable. The approach is far less sensitive to hyperparameters and sampling temperature than PPO, which can see its performance collapse under different settings. Direct preference optimization, or DPO, is a revolutionary, more direct approach, and today we're going to implement it from scratch to fine-tune the powerful LLama 3 model. In this video, we'll cover the entire pipeline. We have already explained the theory of DPO, so we'll dive into the code using cutting-edge libraries like Hugging Face's TRL and PEFT. We'll use techniques like LoRa for memory-efficient training and quantization to make this all possible on consumer-grade hardware. This is a complete end-to-end guide. By the end, you'll have a deep, practical understanding of how to take a powerful base model and align it with your own data and preferences. Let's get started. Before we jump into the code, let's quickly understand the 3 core technologies that make this project possible. First, direct preference optimization, or DPO. Traditionally, to align a model with human preferences, a complex process called reinforcement learning with human feedback, or RLHF, was used. DPO is a newer, more elegant solution. It works with a simple but powerful type of data set, one that contains a prompt, a chosen or preferred response, and a rejected or less preferred response. The DPO loss function then directly optimizes the model to make the chosen responses more likely and the rejected responses less likely. It's more stable and often more effective than RLHF. Second, parameter-efficient fine-tuning, or PEFT, using a technique called LoRa. Fine-tuning a model with billions of parameters would require a massive amount of GPU memory because you need to store the gradients and optimizer states for every single weight. LoRa is a brilliant solution. We freeze the entire pre-trained model. All its billions of weights remain untouched. Then we inject tiny trainable matrices, called LoRa adapters, into the model's layers. We only train these small adapters, which represent a tiny fraction of the total parameters. This dramatically reduces the memory requirements, making fine-tuning possible on a single consumer GPU. Third, quantization. Even just loading a model like LLama 3.8b can take over 16 gigabytes of VRAM. To solve this, we use quantization. We load the model's weights using 8-bit integers instead of the standard 32-bit or 16-bit floating point numbers. This can cut the memory needed to load the model by 50 to 75%. making it feasible to run on more accessible hardware. By combining these three techniques, DPO for effective alignment, LoRa for memory-efficient training, and quantization for accessible model loading, we create a powerful and practical fine-tuning pipeline. So, you want to run this powerful AI model, but maybe your computer isn't quite up to the task? Don't worry at all. We can easily run this in the cloud using Google Colab Pro. The very first thing we need to do is give our project some serious power. Let's go up to the Runtime menu and click on Change Runtime Type. You'll see a pop-up window. The magic happens in the hardware accelerator. Instead of the standard GPU, if you have Colab Pro, you can select the powerful 800 GPU. This is a game changer for speed and will make running this model a breeze. Okay, with our 800 selected, let's get the software ready. We'll run our pip install commands to load all the essential Python libraries for this project. Next up, let's grab the code itself. We'll use a quick git clone command to download the entire project from GitHub. And just like that, we're ready to go. We'll move into the new folder and run the main script. And there it is. The model is running and generating its answer to our prompt. It's that simple to get started, even without your own powerful hardware. Let's start our code journey with dataprocessing.py. This script has one simple but crucial job: to prepare our dataset for the DPO trainer. The DPO trainer, which we'll see later, requires each example in our dataset to be a dictionary containing three specific keys: prompt, chosen, and rejected. Our format example function does exactly this. Let's walk through it. It takes a single example from our raw dataset and the tokenizer. First, it constructs the messages list that represents the start of the conversation. It checks if the example has a system prompt, and if so, adds it. Then it adds the user's question. Second, it uses a very handy function, tokenizer.applyChatTemplate. Every chat model has a specific format it was trained on, with special tokens to denote the start and end of turns. This function takes our list of messages and correctly formats it into a single string, prompt, complete with all the necessary special tokens. We set add generation prompt equals true to ensure it adds the token that signals to the model that it's the assistant's turn to speak. Third, it takes the chosen and rejected responses from the dataset and appends the tokenizer's end of sentence token to each one. This signals the end of a complete generation. Finally, it returns a dictionary with our three required keys, perfectly formatted for our DPO trainer. This function will be applied to every single example in our dataset. Now let's move to the main event, training.py. This script orchestrates the entire fine-tuning process. We start by importing all the necessary libraries. We have Torch for our core deep learning framework, datasets and transformers from Hugging Face for loading our data and models, PEFT for our parameter-efficient fine-tuning, and TARL, which contains our DPO trainer. Inside our train model function, the first step is to set up our tokenizer. We load it from the Hugging Face hub using autotokenizer.from_pretrained, pointing it to our base model. Then we configure it. We set the pad token to be the same as the EOS token, end of sentence token. This is a common practice for autoregressive models. We also set padding side equals left. This is a subtle but very important detail for causal language models. It ensures that when we batch multiple sequences of different lengths together, the padding is added to the left side so the final unpadded token of every sequence aligns on the right. This is crucial for efficient next token prediction. Finally, we explicitly define a chat template. While many models have this built in, setting it ourselves ensures maximum compatibility. This template uses a Jinja-like syntax to define exactly how a list of messages should be formatted into a string, using special tokens like imstart and imend to delineate turns. This guarantees our input is formatted perfectly. With our tokenizer ready, the next step is to load our data and our base model. First, we use load dataset from the datasets library to download our preference dataset directly from the Hugging Face hub. We're using the Intel Orca DPO pairs dataset, which is perfect for this task. Then we use the .map method to apply our format example function to every single example in the dataset. This transforms our raw dataset into the prompt, chosen, rejected format that the depot trainer needs. Next, we load our base model, Unsloth Llama 3 8B. This is a special version of Llama 3 optimized for faster training. Let's look at the arguments to from pre-trained. Device Map Auto is a fantastic feature that will automatically distribute the model's layers across multiple GPUs if you have them, or load it onto a single GPU or the CPU. We also specify torch D-type torch B-float 16. This enables mixed precision training, which uses a more efficient data type for calculations, speeding up training and reducing memory usage. Finally, and this is a critical step for combining quantization with LoRa, we call prepare model for KBit-A training. This function from the PEFT library does some important housekeeping under the hood, like correctly casting certain layers to ensure that gradients can flow properly through a quantized model during training. This makes our efficient fine-tuning possible. Okay, we have our massive Llama 3 model loaded in memory, but it's frozen. We're not going to train its original weights. Instead, we're going to use the LoRa technique. First, we define our LoRa config. This object holds all the settings for our LoRa adapters. Let's break down the key parameters. R is the rank of the LoRa matrices. This is the most important hyperparameter. A smaller R, like 8 or 16, means smaller adapter matrices and fewer trainable parameters, leading to faster training but potentially less expressive power. A larger R, like 64, gives the model more capacity to learn but increases the memory requirements. LoRa alpha is a scaling factor that is often set to be the same as R, and LoRa dropout applies dropout regularization specifically to the LoRa layers to help prevent overfitting. Once we have our configuration object, we call the magic function getPeftModel. This function takes our base model and the LoRa NiCFG and it goes through the model's architecture, finds the target layers, usually the attention layers, and injects our small trainable LoRa adapter matrices next to them. It also handles freezing all the original weights. After this line, our model object is now a PEFT model, ready for efficient training. Now we're at the final setup step before training, configuring the DPO trainer. This is a fantastic high-level trainer class from the Hugging Face TRL, or Transformer Reinforcement Learning Library. It abstracts away all the complex math of the DPO loss function. First, we create a DPO config object. This holds all the training hyperparameters. Let's highlight a couple of key ones. Gradient accumulation steps is a crucial technique for training with small batch sizes. It allows us to compute gradients over several small batches and only update the model weights once, effectively simulating a much larger batch size without using more memory. Gradient checkpointing is another memory-saving trick that trades a little bit of extra computation time for a significant reduction in memory usage. We also set our learning rate, scheduler, and other standard training parameters here. Once our config object is ready, we instantiate the DPO trainer. We pass it our LoRa adapted model, our DPO-ish CFG, our processed dataset, and our tokenizer. One very cool feature of the DPO trainer is that we can set ref model equals none. In DPO, you need a reference copy of the original frozen model to calculate the loss. By setting this to none, the trainer is smart enough to automatically create and manage this reference copy for us, which simplifies our code a lot. After all that careful setup, the actual training process is beautifully simple, thanks to the Hugging Face Trainer API. We simply call trainer.train. This one line kicks off the entire fine-tuning process. The trainer will handle the training loop, moving data to the GPU, calculating the DPO loss, performing backpropagation, updating the LoRa weights with the optimizer, and adjusting the learning rate with the scheduler. It will also handle all the logging and progress bars for us. It's an incredibly powerful abstraction. Once the training is complete, we need to save our work. We call model.save pre-trained open parenthesis output directory close parenthesis. Because our model is a PEFT model, this command is smart. It knows not to save the entire multi-billion parameter LLM model. Instead, it only saves the tiny LoRa adapter weights that we actually trained. This is why our final output directory will be very small, maybe only a few megabytes instead of many gigabytes. We also save the tokenizer to the same directory. This is good practice as it bundles the exact tokenizer configuration with the trained adapters, making it easy to load everything together for inference later. Now that we've fine-tuned our model, let's see how to use it in inference.pe. The load model for chat function handles getting our model ready for a conversation. First, we load our tokenizer from the base model and configure it with the exact same chat template and padding settings we used during training. This consistency is crucial. Next comes the model loading, which is a two-step process. First, we load the original massive frozen base model, just like we did before training. Second, we use PEFT from pre-trained. This function takes the base model and the path to our saved adapter path directory, and it loads our small, fine-tuned LoRa weights and merges them into the base model's architecture. We now have a single model object that has the full power of a Llama 3 combined with the specific alignment we taught it during DPO training. Finally, we switch the model into evaluation mode with model.eval. This turns off things like dropout. We also set useDown cache equals true, which is an optimization that allows the model to reuse computations for past tokens, significantly speeding up the generation of long responses. With our model loaded, the chat function handles the process of generating a single response. First, just like in our data processing step, we use tokenizer apply chat template to format our system message and user message into a single, correctly formatted prompt string. Next, we use a very convenient high-level tool from the Transformers library, the pipeline. A pipeline abstracts away a lot of the manual tokenization and decoding steps. We create a text generation pipeline and give it our fine-tuned model and tokenizer. Finally, we call our generator with the prompt. We pass in several parameters to control the generation process. DoSample equals true tells the model to use sampling instead of just greedily picking the most likely next token, which makes the output more creative. Temperature controls the randomness. A higher value means more random, a lower value means more deterministic, and TopWP enables nucleus sampling, another advanced sampling technique. The pipeline handles the rest, and we simply return the generated text from the output. Finally, we have main.py, our project's entry point. This script serves as a command line interface, or CLI, that lets us control our entire application from the terminal. We use Python's built-in argparse library to do this. First, we create our parser. Then we add all the arguments we want to be able to control. The most important one is mode, which is a required choice between train and chat. This single argument will determine what our script does. We also add arguments for things like the base model name, the dataset, and the user message for chat mode. After parsing the arguments provided by the user on the command line, we have a simple if-else block that acts as a router. If the user ran the script with /mode train, we call our train model function from training.py passing in the relevant arguments to start the fine-tuning process. If the user ran it with double-dash mode chat, we call our load model for chat and chat functions from inference. Pi passing in the user's message to generate and print a response. This simple, clean structure allows us to manage both training and inference from a single, easy-to-use command. So let's take a moment to recap the powerful and modern fine-tuning pipeline we've just built. We've gone deep into direct preference optimization, learning how to use preference pairs to effectively align a language model. We've mastered an incredibly efficient workflow using quantization to load a massive model into memory and then using PEFT with LoRa to fine-tune it with minimal resources. We've structured this all into a complete application with clean, modular code for data processing, training, and inference. And finally, we've tied it all together with a flexible command line interface. You now have the knowledge and the code to fine-tune state-of-the-art language models on your own custom data. I highly encourage you to experiment. Find a different preference dataset on the Hugging Face Hub and try training with it. Tweak the LoRa rank R and see how it affects the model's performance. As a great next step, you could even take the inference Pi script and wrap it in a Gradio UI to create a shareable web demo of your custom-tuned model. Thank you so much for joining me on this deep dive. If you learned something valuable today, please give the video a like and subscribe for more tutorials on cutting-edge AI techniques. Happy fine-tuning!